use it. And so this flipped everybody round from just communicating with the TPM as an ordinary clear text device to assuming that the communication channel of which you talk to the TPM is potentially compromisable. And if you're sending secrets over it, like systemd has the unlock key for your operating system, for instance, you don't really want an attacker attaching a small device and just snooping the bus and getting that. So the only attack that has been demonstrated so far is what's called a passive interposer attack. It's just a little device that snoops and does nothing. These are actually very easy to defeat. All we have to do is encrypt the traffic on the bus, and the snooper can't see it. It's very much like using HTTPS. Once you use HTTPS instead of HTTP, the man-in-the-middle attack is thwarted because the man-in-the-middle can't see your communications. But an active interposer would be something that acts as the endpoint for that traffic. It's sort of like having an HTTPS endpoint sitting where you didn't think you were going, which is why you always verify the server certificate, and then retransmitting your commands onto the TPM. And it can do that with encryption, because if it acts as the endpoint for your TPM communications, it can pretend to be the TPM you think you were talking to. And we don't really have an infrastructure like server-side certificates in the TPM. We do have other means of identification. Slight problem is nobody uses them, but I'll get onto that later. But in order to get a TPM to encrypt traffic in the first place, you actually have to set up that encryption. The way you set up that encryption is something called TPM sessions. These work effectively by establishing a shared key between the application and the TPM. It's called the session key, and the TPM has a very complicated rolling encryption scheme. The session key is basically a salt from which key derivation functions are applied to nonces that are exchanged on the bus. It's one of these really, really complicated schemes. But the bottom line is, if you know the session key, you can decrypt the traffic. And so the object of all of this, the complexity of the encryption key scheme actually doesn't matter at all. The object of the attacker is to gain your session key. And the initial session key for a TPM is something called, in TPM terms, either bound, which is a shared secret. It's sort of like a WEP key for the wireless. It's something both you and the router know. And obviously, in order to have a shared secret with the TPM, you've got to have communicated with it before, which often isn't the case for applications that are very ephemeral. Or you can use something called a salted key, which basically means that I have a secret the TPM knows, I encrypt a key to it, or I encrypt a nonce to it. That nonce becomes a salt for which all the sessions are derived, and that's the way I communicate in secret with the TPM. And sessions were actually added to all Linux kernel TPM transactions in the kernel 6.10, which is now about 2 years ago. That was all my code, so I actually wrote all of the code that does this. It's under a bit of attack at the moment because one of the prices you pay for adding sessions to the TPM is that all TPM operations become slower because you have to encrypt on your end, and the bigger problem is the TPM, which, if it's a discrete TPM, is a very low budget, low energy device, has to decrypt on its end. And the problem is usually it decrypting on its end because it just takes it a long time. But what's often not understood is that there are actually security problems with the way you set up TPM encryption, even with salted sessions. Because although a salted session is I encrypt to a public key of the TPM, so all I have to do is ask the TPM for that public key. I encrypt to it and I send my encrypted packet to the TPM. The question is, how do I know that the public key it gave me is the one I'm supposed to have? Because if I have an active interposer sitting in the middle, it might have lied about the public key, just given me a public key it knows, and therefore it will decrypt my salt. It will intercept all my transactions and pass them on to the real TPM as though nothing had ever happened. One of the problems, if you actually look at a lot of systems that claim to use TPM sessions, usually you use a library and user space when communicating with the TPM. And I should add that all of the protections I did in the Linux kernel only work for the Linux kernel. The sessions have to be set up by the application using the TPM. So when the kernel itself uses the TPM, it's the application, it sets up the sessions. But when you're using them in user space, like say systemd using the TPM to get the encryption key for the disk, the systemd itself is the application. The kernel can't add encryption to it. It has to do this all on its own. So this also becomes a scalability problem. The way user space communicates with TPMs is something called a TSS, which is a trusted secure stack. It's a library for communicating with the TPM. And the way that the trusted secure stack in pretty much every implementation, and there are two separate trusted secure stacks out there. There's one written by Intel and one written by IBM. Intel is the one that's most often used. The way they get the public key for encrypting sessions is to ask the TPM. And as we know, that's a bit of a problem. So, as I said, the active interposer can intercept the ask, supply its own key, and decrypt the salt, decrypt all the sessions. All of your illusion of security is gone, even though you think you're using it correctly. And like I said, most TSSs don't even make it obvious that this problem occurs. Most of them will just quite happily, you use the correct API, it sets up the session. I mean, the problem with the TPM is TPM programming is astronomically labyrinthine difficult. So you use this toolkit to make your life much simpler, and this toolkit doesn't do it right, and that's a problem. And obviously, the real problem is that none provides any verification of the key that you're actually using. That public key, how do you know it's the right public key? Obviously, there are other problems with the interposer. I mean, even a passive interposer just sitting on the LPC bus can actually toggle the TPM's reset line. Part of this problem is one of the jobs of a TPM is to store things called PCRs, which are registers that extend via a hash and in theory never go backwards. So you use a PCR to build up logs of what happened on the system. And the PCR value is validated against the log. This proves that all of the stuff that exists from boot to whenever you currently are is valid, happened, and the log hasn't been tampered with. This is the way a TPM protects a non-repudiable log. The property that relies on is the fact that the PCRs can never be reset. They never go back to zero. Problem, if the interposer toggles the TPM's reset line, all of the PCRs go back to zero, and you've lost all of the security you had in your logs as well. And even a passive interposer can do this thing. Like I said, they all go back to zero if you toggle the line. And obviously, if you control the operating system in just a small part, you can reset all the PCRs, rebuild them to where they should have been to say that you're legitimate, intercept all the logs, and nobody would be any the wiser. So one of the fundamental questions that we really need to understand is how should you establish trust with a TPM? And there is a provided mechanism. It's so complicated that no one ever does it, which is why the TSSs don't do it. But all discrete TPMs ship with what's called a manufacturer certificate. That manufacturer certificate validates something called the endorsement key that is resident inside the TPM. And that certificate via X509 chaining goes all the way up to the manufacturer's master CA. So once you have a TPM, if you know what type it is, you go to the manufacturer's website, get their CA certificate, validate the certificate your TPM gives you. So an interposer can't give me a false certificate because I'm validating it against the manufacturer's CA. And that validation tells me what the endorsement key of the TPM is. And that gives me one public key in the TPM that I know absolutely works. Problem here is that the certificates certify the endorsement key. That key can't be used to certify any other objects in the TPM. This turns out also to be a significant problem because the usual object you encrypt the salt to is actually the storage key, not the endorsement key. It doesn't mean you couldn't encrypt to the endorsement key, but the problem is that most of the time you're playing with the storage hierarchy of the TPM, not the endorsement hierarchy, so the TSS naturally encrypts everything to the storage key, which is, even if you validated the TPM certificate, not a key you've actually certified from the TPM. The TPMs themselves actually generate primary keys from a seed using a key derivation function. This is what allows for crypto agility, because if I want an RSA key, I take the seed, generate prime numbers from it. If I want an elliptic curve key, I just feed it into the elliptic curve routines. The point is that seed doesn't change, and so the keys I derive from it are always the same, no matter what algorithm I ask the TPM to use. And one property of a TPM key, a primary key in the TPM, is that they can either be signing keys or they can be encryption keys. The endorsement key that the certificate certifies is actually an encryption key. The problem with a TPM is when a TPM certifies other objects in the TPM, so like I want to encrypt a key to the I want to encrypt my salt to the public key of the storage root system, I want the TPM to give me a certificate saying this storage root key is valid. It can do that, but it can only do that if I know a signing key. And the only key I know from the certificate is an encryption key. So how do I get around this? Well, let's go back and ask why we don't actually have a signing key as part of this certification. It turns out it's all the FSF's fault. The Trusted Computing Group actually got badly burned by the FSF backlash against something they called treacherous computing way back in the early 2000s. Because the TPM was mooted as this instrument that would be used for, content certification, preventing you from watching videos, etc. It's all actually untrue. The TPM is too weak an encryption engine to do this, but it was seen as the spy on your computer, and the FSF made a lot of fuss about it. They actually coined a phrase called treacherous computing instead of what the Trusted Computing Group was trying to call it, which was trusted computing. The fact of the matter is that TPM will work on behalf of anybody who has access to it. You own the operating system on your computer. You're the one guarding the access to the TPM. Nobody else can use it unless you actually give them permission to. And so treacherous computing was not, there were definitely plans of operating systems that weren't open source to use TPMs for various nefarious purposes, but they rapidly got killed by this campaign against it. So even Microsoft nowadays is very careful to give you the ownership of the TPM in Windows rather than just taking the ownership itself and controlling your TPM. But obviously, as most of you here should be running Linux, that's not even a problem you need to consider. You own the operating system, you own the interface to the TPM, you own everything that goes on with that device. Like I said, they criticize the TPM as an agent in your PC acting on behalf of others, but it can't communicate with the outside world except through the operating system. So if you control the operating system, you absolutely control it. To counter this, the TCG, the Trusted Computing Group, tried to introduce privacy-preserving features of the TPM. One of those privacy-preserving features was not allowing manufacturers to certify signing keys. The reason for this was because if the manufacturer gave you an easy signing key, that's the key you'd use for all certifications in the TPM, and that would mean that you'd be able to be tracked online by the certification you just gave, which is tied back to the endorsement key that every manufacturer of the TPM knows. So this would be a unique tracker in your TPM that allowed anybody online to track you via TPM operations. And therefore, because it's a single signing key, it would have uniquely identified you. So the Trusted Computing Group said, we're not going to do this. We'll allow you to create a large number of possible attestation keys in the TPM. We'll introduce something called a privacy CA, which will link the attestation key in the TPM that you can create to the endorsement key that's only an encryption key, and the privacy CA will do the linking, so only the privacy CA will have this information, and the privacy CA would be a trusted third party that's trusted both by you in the operating system and by whatever on the internet is asking for certification. And whatever on the internet is seen is a signing by an attestation key that you've obtained from the privacy CA that has a certificate saying the privacy CA trusts this, so you can trust me. And obviously, only the privacy CA then is the thing which can track you, and thus could track the user. And so this should eliminate a lot of the complaints the Free Software Foundation had about treacherous computing. And obviously, they had to introduce a load of special TPM operations. These are operations called make credential, activate credential. You don't need to know anything about how they work. But the point is, they are operations you can use to create ephemeral signing keys, which can then be used to certify objects in the TPM, which is really what we want, because we want to know that the storage key belongs to my TPM. Oops. So, problems with this. Privacy CA idea has been around for 10 years. None exists today. Nobody ever thought that this scheme would work, or at least nobody bought into this scheme enough to actually run one of these things. So this is now a system that all TPMs support that we can't use in practice because we have no privacy CA. For my purposes in the kernel, even if privacy CAs did exist, I can't use them because in early boot, the Linux kernel does not talk to the internet. You know, it's a booting kernel on a chip. I have no way of contacting a privacy CA at start of day in the Linux kernel. So even if we had them, I can't use them. And one of the things we could do inside the Linux kernel is we do have X509 code that can do certificate validation. If I manage to find all of the master CAs of all of the possible manufacturers of all TPMs, it's theoretically possible that I could validate the endorsement key just using X509 certificate validation. If I could do that, I could actually use the endorsement key to encrypt my salt to. I don't really need to encrypt it to the storage key, which is what everybody else does. But the problem with this is when we were first doing this, there were a large number of manufacturers of TPMs. Nowadays, they all seem to have consolidated to about 3 or 4 Israeli and other companies, so it may now be possible to do this. But when I was first coming up with the kernel mechanisms for doing this, it wasn't really possible. And the other problem is, as I said, I've got a firmware TPM. Firmware TPMs often don't even have endorsement key certificates. So if I boot Linux and I find you don't have a certificate, what the hell do we then do? So given all of these problems, we actually needed to come up with a new scheme. And the kernel solution was to use something called the null primary for session salting. So here's some more TPM trivia. The TPM itself has 4 separate hierarchies. These are designed for different users of the TPM. There's something called the platform hierarchy, which is only supposed to be used by the BIOS. After the BIOS is finished using it, it puts a random password in the platform authority, which means nobody else can ever touch that hierarchy. The endorsement hierarchy, which is where the endorsement key lives, but is otherwise not used, is designed for attestations to outside bodies. So you're not really supposed to touch it unless you're actually doing an attestation to an outside body. The owner or storage hierarchy, which is where keys are normally stored, is the one that you as the owner of the platform actually get to use. But then there's a 4th hierarchy called the null hierarchy, which is normally never used. The interesting property of this null hierarchy is that anybody can use it, but its seed changes on every reset, which means that if I encrypt a key to the null hierarchy and reset the TPM, I've lost that key because the TPM then can't unencrypt it. So this is often seen as a useless hierarchy for long-lived keys, but for operations that only last for the boot of a machine, which the null seed won't change over, it can actually be used. And like I said, the interesting property is this seed changes on every reset. So if I salt all of the sessions to the null seed and somebody resets my TPM, that salting will suddenly fail. And so the kernel will actually get wind of the fact that somebody has activated the reset line. And so this is the reason that we actually salt sessions with the null seed in the Linux kernel. But obviously, we can do this easily. We ask, but we still ask the TPM, what is your null key? And it gives me an answer. And we still need to know that this answer is correct. And like I think I've demonstrated, there's really no way of doing this at boot. So the best scheme I can come up with, like I said, it will reset will tail. We can detect a reset attack. We export the name that we actually saw on boot to a sysfs file. Names of keys, by the way, is just a hash of the public area of the key. So it's a unique identifier per key. So once I have the name, and if I had the way of certifying the null object, I would then be able to completely validate that I booted up with the correct null key. And this is actually what we do. So we can verify this null name that the kernel exports by more sophisticated means, but I can only really use those sophisticated means after the kernel is booted. So as long as I trust my kernel and user space, I can get conclusive proof that the system booted up correctly, but at the time the system is booting, the kernel still has no idea that it hasn't been intercepted and it is booting correctly. But we do have enough information to do this verification after the fact. What I actually did was, okay, so the OpenSSL TPM2 engine is the toolkit that I did primarily for using a TPM through OpenSSL. It provides both an engine and a provider for OpenSSL version 1 or version 3. But it also has a set of cool toolkit stuff for allowing you to manipulate TPM keys. One of the additional binaries I added was something called a test TPM2 primary that allows you to do all of these attestation operations. And it actually has 3 functions. One is --EK sign, which actually works out if we'd had a signing EK instead of an encryption EK, what would it look like, and just give me the name of it, which is an easy thing to do. A test which actually runs the make credential, activate credential, produces an ephemeral key, validates the EK signing key, and then says that either this key conforms to your certificate or doesn't. So now we have bound the signing EK directly to the certificate that is sitting in your TPM if you run this. And obviously, this only needs, if you can store the signing EK, its name, somewhere in an immutable part of your operating system. So it should be installed at time of install of the operating system, and it's never modified. You can rely on this evermore. You only really need to do this attestation once. So we could do this as part of operating system install and then forget it thereafter. And then there's a certify function, which is used to certify, based on the EK signing, the signing EK key, all other TPM objects. Obviously, the original problem that the TCG had does not exist here, because I'm the person who created the signing key. I own the laptop. It doesn't really matter if I track myself, so I didn't really need to do any of the other CA stuff. So once I have the EK signing key as the owner of the operating system, that's what I use, because I'm using it for my internal purposes. I'm not using it to certify to anybody else. There are no privacy concerns. So what are the threat models? Obviously, running this tool means I have to trust the operating system. And the TPM people would tell you the TPM is the only way of trusting your operating system, but that's not true. We do have secure boot people who often don't talk very well to TPM people. But if you're securely booting your laptop, secure boot validates the fact that you have booted the correct kernel. And if you're using UKIs, it can be used to validate the initial RAM disk as well. As long as you have full disk encryption, the fact that you had to type a password to decrypt user space validates user space. That gives you sufficient trust actually to validate the TPM after the fact. Even if there's an interposer from an evil-made attack sitting in your computer, you would now be able to detect this, as long as the interposer, which is a fairly weak thing, can't compromise your kernel sufficiently to get to the result of this, the certification that you're going to do. Obviously, this verification is ineffective unless you trust the operating system. So if somebody steals your laptop and turns off secure boot, substitutes their own kernel, defeats all of this, and manages to get your disk encryption key, it's game over. This is one of the reasons why, by the way, although I'll be showing in the demonstration, hopefully I've got time to do it, the fact that we can just do a complete unlock with a TPM using PCR values, you should never do this. You should always have a second factor in a TPM unlock that ensures if somebody steals your computer, they can't then, through means of intercepting the kernel, damaging secure boot, etc., unlock it. So always use a PIN. And make sure that PCR7, which is what attests to secure boot, is part of the policy check of systemd. So, if I'm lucky and I've got enough time, we will try and do a demo. So, first of all, I'll start a software TPM. So this is the IBM software TPM. It's very useful thing for checking. I'm actually also going to start an interposer here. So what's going to happen is my virtual machine is going to talk to the interposer, and the interposer is going to be the thing that talks to my TPM. So I've already set up an actively interposed TPM system here. And then in my VM console, I will start the virtual machine. Oops. Oh, do excuse me. Sorry, I had my virtual machine operating. Okay, here we go. So this is actually going to boot up. This is an encrypted disk image, but I've actually set it so that the disk encryption will release the TPM key based on PCR registers. So it's already actually released the disk encryption key, and it's going to boot me straight into user space. So there I am. And I can log into this now. I'd ignore that. I have so many virtual machines sitting on my laptop that security for this one system is actually disabled. And so what I'll do is I will demonstrate, first of all, what kernel am I running? So I have to apologize. That is 1 week old. It should be RC2 now, and it's RC1. So this is the latest Linux kernel. I actually have all of this stuff turned on, so if I go to so this is where you find the name of my system. So this is the null seed that it used to boot up with. Now, we're going to pretend that all of this is secure and I've done it. So one of the first things you should always do is, on first boot, I would have got the EK signing name and put it somewhere where I know that can't be tampered with. So it's on the encrypted file system. Unless somebody compromises my encryption, they can't change this file. This is the name that I'm going to use to validate everything. And obviously, this is a software TPM, right? So it has no certificate. But Ken Goldman, who's IBM's TPM guy, gave me a mechanism for actually giving this thing an endorsement key certificate. So it actually has a real endorsement key certificate that I can get out of it. So this is the index, or so that is a known place in the TPM NVRAM where the certificate is supposed to be stored. It comes out as DER. I've actually asked the TSS NV read to translate this to a PEM certificate, and we can actually have a look at this PEM certificate. I can just translate it to text, the one I got. As you can see, it was issued by IBM Yorktown Heights, which is where Ken Goldman works. It's EKCA, so if I trusted this EKCA, which obviously I created, so I trust it, I would validate the certificate, and it would then give me a signature over the TPM endorsement key, which is what this is. And then all I would do is run an attestation. Using that certificate and comparing it against the signing EK name that I've already created. And this is actually going to run a make credential, activate credential. You notice there was a slight delay there. It took about 100 milliseconds to return. That's because even for a firmware TPM, this round-trip operation is quite expensive. But now I validated my signing EK against the endorsement key certificate, so I'm now completely confident that the EK name I have is the correct name. So every time I ask a TPM to derive an EK, I just ask it, what is your public key? Take the hash of that. That hash gives me back the EK name. Actually, I'll show you what they look like. All it is a 4-digit prefix, which is a 16-bit version of the TPM hash. And the rest of it is a SHA-256 hash of the key. That's it. That's all the name is. But I can use this name to certify the null key. So I ask the test TPM2 primary to certify the null against the EK signed name. So what it's going to do is ask the TPM for the signing EK, get it to construct it, compare what it gives me against the name that validates it. Then it's going to use the key that it just constructed to issue a certificate, and the certificate is actually signed by the private part of the endorsement key, the signing endorsement key. So I know that only the TPM can have actually issued this signature. I will validate that signature in user space. That validation I will then compare on the null name, and if the two match, everything is correct. And actually, that takes a lot less time than the attestation did, and it gives me a good certification. So now I know that my kernel actually booted up correctly, which you wouldn't have expected given the fact that I actually have an interposer in the way. But the point is, I wrote this interposer so that it wouldn't be detected. So it knows what a kernel TPM transaction looked like, and it stays the hell away. All it's doing is acting as a conduit, passing these transactions to the TPM. Now, this means that it can't snoop, it can't steal anything, it can't do anything, but it's waiting for another subtle event where it knows it can steal my credentials. And so we'll get onto that subtle event now, which is I'm going to take this system and I'm going to tell it to change the TPM-based disk key using crypt and roll. And to do that, I'm going to have to, my system is actually locked against PCR7. I'm going to lock it against PCR9, otherwise systemd would cleverly refuse to enroll this. That is going to be systemd going through the, also going through the interposer. I need my disk password in order to do the enrolling. And there it goes. It's wiped and re-enrolled the key. Problem here, systemd just asked for the, it actually asked for the SRK, and it used what the TPM told it, and it didn't validate that against the certificate. So what happened is my interposer here actually did a substitution of the key that systemd asked for. Once it's substituted, it can snoop the transaction. This thing here is actually the disk key that systemd tried to seal into the TPM. And I can prove that by taking a copy of this. And if I do if I just do crypt setup verbose open, ask it to test the passphrase on the disk, and then I'm just going to insert that passphrase. I've done a copy and paste on my keyboard, which you didn't see. It validates that, and I have successfully unlocked the disk. That proves that I just used an interposer to steal systemd's disk key, which also proves that TPM security is something that everybody should really take rather seriously. Now, as a final thing, because I am running out of time, I will try and do a reset of the TPM, because remember, I promised you that this system would detect resets. Fortunately, resetting a software TPM is very good, very easy. I just tell it to power up and start up. If I look in the VM, at PCR9, which is what I locked it against, has gone back to 0. Now, if I look at the kernel actually hasn't noticed this yet. If I have time, I will run a certification. And the null name has changed. So the certification is actually failing because I have the wrong null name. And that proves the fact that if I'd done this, I would have been able, if it had actually done this in the kernel, it would have been able do it. And now the kernel has actually detected here that the integrity of a TPM transaction it tried to do has failed. And the next thing the kernel is going to do is disable the TPM because we're under attack. So if now I ask it for register 9, it won't give me it because I can't talk to the TPM anymore because the kernel is preventing me. So this is a demonstration of at least some of the security procedures we've put in place inside the Linux kernel for all of this. And with that, I will try and get on to the conclusions and give you time to ask a few questions. I think I did manage to go fast enough that we do have time for questions. So, the null seed is an interesting scheme, but it does fully protect us from reset attacks, as I demonstrated. After boot the verification after boot proves that the boot you did was fully secure, provided the kernel and user space are trustworthy. So you still are resting that trust in both secure boot and encryption. If you don't have either of those, you've probably broken this trust requirement for doing the verification. So it's very important that you do that. Any TPM tool could actually use the null key for salting, and what that means is that if you do use the null key in user space applications, you can actually compare it against the null key the kernel is exporting and be guaranteed, as long as you did the check at start of day, the certification at start of day, that you've actually got the correct null key for salting. And this would mean that everybody who's actually using, all applications using the TPM, having to create their own sessions, could then be secure both against interposers and against reset attacks. It hasn't happened yet, but I'm hoping one day it might. And obviously, you can simply verify the calculated name against sysvs file for the null name, so you always know if it's correct. And thus, full safety is always extensible to every TPM tool. With that, this is an impress.js presentation. These are the URLs for both the presentation and the interposer. It's all available as open source. I mean, that Git repository is a bit thin. It's got about 10 commits in it because it's just what I did for a demo, but you're welcome to look and play with it if you like. And with that, I'll say thank you and call for questions, if there are any. Okay, first question. Oh. So the question is, could we use the null seed in association with systemd boot parameters to do more key derivation that would actually give us secure keys? The answer to that is actually yes. There's a guy called Ignat Kochagin who's exploring stuff like this. He wants to use it for something he's calling, it's some kind of key that goes in the kernel. I've forgotten the name he gives to it. But it is perfectly possible, but you have to remember the limits of these keys you've derived. That null seed only survives one boot. You can't use it for any information you want to persist beyond that boot. Yep.
So in your demo, you had your interposer compromise the key and pull out the disk encryption key from the transaction. But then it takes a little while for the kernel to actually notice and lock down the TPM. Is the idea that that window is just so short there's not enough time for anybody to do anything, or are we just kind of implicitly accepting that within this window there are things you can do, but we hope that you aren't that fast?
Right, so the question is based on the observation that the kernel takes a while to note that the TPM has been compromised by a reset attack. But the other part of the question was, you noticed that I pulled out the key, and but that wasn't done via a reset attack. That was by a different vector of the interposer. Remember, the kernel operated perfectly normally for boot up while the interposer was there. I cleverly programmed my interposer only to steal the systemd key and not to reveal its presence to the kernel. So it doesn't do anything that the kernel is looking for. And it does this by ensuring that all of the kernel transactions are perfectly integrity protected, because systemd is the one which has the important transaction that has the key I'm after. So to go back to your first question, the delay in detecting is because the TPM is a polled device. I have no means of getting it to tell me immediately if something is compromised on it. I have to wait until I ask. And right at the moment, the kernel asks the random number generator every 30 seconds to reseed the entropy from the TPM. That transaction is protected by sessions because obviously we don't want entropy leaking from the kernel. And when one of those fails is when I notice. But you're right, in that 30-second window, like I had when I did the certification and it failed and I showed you the value of PCR9, if you can get your TPM exploit in that 30-second window, yes, you're right, you can do it. Yep.
So I'm stuck in the ARM world.
Well, you have my deepest sympathy. We all like ARM now, though.
So, a lot of this TPM stuff, it's because x86 standardized around UEFI, and UEFI is tightly coupled to the TPM. How can I get the same goodies in ARM?
Well, so the question is, what if you come from the ARM world, because this is fairly x86-centric? The answer is that actually the ARM world does have a lot of systems with TPMs. I have several developer boards, I think the Potato board and a few of the other ones. They actually do have discrete TPMs sitting on the board. The other thing is that UEFI, it doesn't really have a tight coupling to the TPM. So if I disabled my software TPM, my virtual machine will still boot up without it. UEFI will detect the fact that I don't have a TPM and just turn everything off. All UEFI uses the TPM for is the measured boot log. Because UEFI is the first booting section of the kernel, it begins the measurements and it builds up the measurements into the PCRs, the measurement registers. So if you disable the TPM or don't have one, all you lose is the fact that you don't have a measured boot trail. But there are a lot of ARM systems that are UEFI-based because UEFI is starting to be the default for ARM64. So a lot of the ARM, it's probable there will be no ARM32 systems with UEFI and universal mechanisms, but everybody is starting to adopt ARM64 as well. I mean, my phone has ARM64, but obviously it doesn't have UEFI, but a lot of the server-class systems that are trying to be sold, I do have UEFI. They are interested in using measured boot techniques, so they're interested in having the TPM and the ARM-based UEFI actually do all the measurement stuff. So a lot of the server-based ARM systems are starting to look like x86 in this respect. So as long as you have the right ARM system, you can actually do all of this as well. Oh, same with RISC-V. I mean, I'm not a RISC-V person, but it's basically driven because they need compatibility with all the x86 stuff. There are lots of people who demand the integrity that measured boot gives you, and either ARM and RISC-V or whatever would go off and reinvent their own system and everybody would complain like Billio because we have one that works, or you just follow the least line of resistance and use the one that works, which is what ARM64 and RISC-V are doing. Okay, I need to give you at least 5 minutes to change rooms, so with that I'll say thank you very much and I hope you enjoyed the presentation.
Hello? Yes.
Oh, it's scratching your visitor. No, it's okay. Leave it. Yeah. Great. I wiped it before. Great. So
Thank you.
it's okay?
Yes.
I'll check in to make sure you're off and running in about 10 minutes. No problems. But
Okay.
you're not doing any audio, right?
No, no. Okay, thank you. Hello, everyone. So I think we can get started. And thanks for coming to my session. And I'm very glad to be here. And I'm very glad to have this opportunity to share my multi-kernel Linux-related work with you today. So let's get started. So before we get started, so just a quick introduction. So my name is Kong Wang, and I'm a Linux kernel developer. So currently, I found my company, Multikernel Technologies. So this is why I'm here today. So multi-kernel, so I know this idea maybe not sounds familiar to you. However, before we start, so the first thing I want to clarify is this idea is definitely not new. So this idea actually is pretty old in my opinion. So at least this idea dated from 2009. So the first paper established this idea and pioneered the multi-kernel operating system work is called Ballroom. So it was in 2009. So and it is a completely new operating system, and it's definitely not a Linux. It's the operating system written from scratch. So this is probably the first multi-kernel operating system implementation, at least according to my research. However, this work is mostly stay in the academic research, is not in production. And the second work I want to mention is the popcorn Linux. So this one deserves attention because this one actually is the first multi-kernel implementation with Linux. And this work was in 2017, which is also old, right? And however, the main purpose of this project is targeting the heterogeneous CPUs, and based on my entire career, I have never seen such heterogeneous CPU in my entire career. So that's why I have, a very different opinion with the direction of this project. And another project that needs to mention is the Meg kernel. So Meg kernel is kind of Linux and also kind of not, because it's a mix. So my Meg kernel is actually, they build another kernel on top of Linux, and that kernel is very lightweight. And that kernel actually only provides the necessary high performance layer for the application running on top. And so that's why it only provides about less than half of the system cores of the Linux operating system. So if the system call is not implemented in the Meg kernel, it is simply just forward the system call to the actual Linux. So this is how it works. And as you can see from this very short history, so multi-kernel actually has a very strong interest, at least in the academic research. And so what's different with our approach, and why it is different now? Because the approach we choose actually is very different from the previous work and previous project. So first of all, the first multi-kernel implementation I mentioned here, they all take the replica-based approach. That means the different kernel, although they are separated, however, they share all the replicated states. So we took a very different approach. We use the multi-kernel as isolation, so we don't use any replica. And another significant difference with all the previous project is we developed on top of the upstream Linux from day one. So we don't write the operating system from scratch, and we don't write, any out of tree code, and everything is based on the very latest upstream. And more importantly, actually, we don't have any compatibility issue compared with the Mac kernel. So that means everything you have today running on top of Linux, it should continue work on our multi-kernel Linux. So what is multi-kernel Linux? So let's get back to the idea, down to the very minimum core concept. So multi-kernel actually is a very simple concept at the core. So the idea is pretty much just run multiple Linux kernel simultaneously without using virtualization. So this is the entire idea. And we compare with virtualization. The advantage is all the multi-kernels are running on the real hardware, on the bare metal hardware. So there is no virtualization overhead. And all the hardware resources, they are participated and dedicated, allocated to each of the spawn kernel. So each of the kernel gets their own CPU, memory region, and device resource. And ideally, each of the applications, they should run inside each of the kernel. And the advantage of this actually is the kernel could be just tailored specifically to run the specific application, and we could also specifically optimize and tune for that specific application as well. And more importantly, everything is Linux. So the spawn kernel actually could be just the Linux with only the multi-kernel support. And that means we have the complete compatibility. So with this idea, ideally we should could run the different workloads on the same node and with multi-kernel as the isolation. So how does this work? So this sounds pretty cool, but underlying how does this work? So for the implementation, actually, it's not easy to put all the pieces together. And the first thing we need to solve is how to start multiple kernels simultaneously on the same host, right? So the infrastructure is there because Linux already supports the kexec mechanism for decades, and the kexec works, and it only currently it could only start a new kernel and replace the old one. However, for multi-kernel, we definitely want to keep the old kernel still running and launch multiple kernels together. And also without a hypervisor, that means we need to have some way to partition all the hardware and without using virtualization. And resource partitioning is another challenge because it's not just we just simply allocate the resource. It's also we need to manage, for example, the conflicts. For example, when we allocate the memory region, we need to avoid memory region conflict between different kernel instances. And this is also a very big challenge we have solved for the multi-kernel architecture. And the last thing we need to solve is dynamic resource isolation, because static resource isolation is pretty easy. That's pretty much the default what we get when we start the kernel. As long as we don't change anything during the runtime, we by default get the static partitioning. That already works, and that's the easy part. The hard part is, after we start the kernel instance, how do we update the kernel instances without shutting them down, right? So how do we move the CPUs from one kernel instance to another? How do we update the memory of one instance and maybe assign it to another kernel instance? So this is another big challenge we also have solved with device trace infrastructure provided by Linux kernel. So this is the overview of the entire architecture. So I hope this picture could clarify what I have mentioned, how the resource, specifically how the CPU cores and memory regions and, different kernel binary, different kernel regions, how they are partitioned. So this is a very, very high-level overview of the entire multi-kernel Linux architecture. And so why do we need this multi-kernel Linux? So it maybe looks cool, but why do we need this? So I do have about 4 use cases here. So because like I mentioned, multi-kernel is pretty much targeting the isolation. So isolation is pretty much the foundation for the cloud computing today. So for cloud computing today, we have pretty much, there are 2 major technologies, right? So the first one is container, and the second one is virtual machine. So, and also, of course, we could also combine them together in some way, right? Some, Kata container actually run containers inside a virtual machine. So, and people call it a secure container, whatever terms. So, and compare with the existing technology for cloud computing. So what are the advantages of multi-kernel? So let's take a look at them and compare with them one by one. So compare with container, and the advantage of the multi-kernel actually is stronger isolation and more secure. So that's why I believe multi-kernel is stronger than container. So as people probably already know, containers, they share the same Linux kernel. So the problem with this approach is the kernel has some security issues. That means that security vulnerability will affect all the containers on the same node, that's for sure. And another issue with the container is the resource isolation. So the reason why container is much lighter than virtual machine is virtualization is based on the resource. Is based on the software resource isolation. The software resource is provided by the Linux kernel, and the problem with this approach is known as a noisy neighbor. So if one container could produce a lot of noise, so that means they would eventually have the resource contention in the kernel layer. That means the resource contention will definitely slow down other containers on the same host. So this is typically called noisy neighbor. And compare with container, the advantage of multi-kernel is first thing is we don't have any software resource isolation. So it's the kernel level isolation. So because each of the workload gets its own Linux kernel, and the kernel is isolated. So that means we don't have the noisy neighbor issue as long as we have separate kernel and separate hardware. And the second advantage is because the kernel is also separated, if one kernel has some security vulnerability, it definitely won't affect other kernel instances if they have different kernel versions. And the last advantage is actually because we have different kernel, and the kernel could actually be optimized, tuned, and tailored down to the minimum specifically for the workload, the target workload you want to run. So this is definitely what the container could not achieve. And let's take a look at the virtual machine. So virtual machine actually is pretty strong. So in my opinion, so it's not very easy to compare with virtual machine, to be honest. However, virtual machine also has some limit. And virtual machine, so the first one actually is because virtual machine use virtualization. So virtualization has overhead. I know today, we have the hardware acceleration for the virtualization. However, even with the hardware acceleration, we still have some overhead, maybe already down to 5% or something. However, it is still there, and for some cases, it still matter. And another advantage actually maybe is not obvious. However, it's very real. It's the network virtualization. So this is real because today many companies already have their servers in the cloud. So, and when we purchase cloud from the cloud providers, we already pretty much by default get a virtual machine. So if we want to run another virtual machine inside the cloud we purchased, that means we get a network virtualization. For example, we have AI agent today. So, and AI agent runs in a sandbox. So if that sandbox is a macro VM, and if you want to run your sandbox inside your cloud, that means you have network virtualization. And this advantage is much more obvious than just, compare with the virtualization on the bare metal, because the network virtualization first, the overhead is much higher, probably 40% or something. And the another advantage is actually the support for network virtualization is not mature. So not all the cloud providers support network virtualization. So even Amazon actually just supported the network virtualization very recently. And so this has been a pain point for the cloud providers for a long time. And the last limitation of the virtual machine actually is virtual machine is a complete OS. So that means typically, unless you use macro VM, we would go through the entire operating system initialization. So if you use systemd, good luck on the booting process. And so compare with virtual machine, the advantage of a multi-kernel is there is no virtualization overhead. And especially if you run multi-kernel inside your cloud, which is a virtual machine, you don't have any necessary virtualization at all. And multi-kernel could boot directly into the Docker image. So that means there is no operating system initialization at all. So speaking of Docker, so we all like Docker probably, right? So Docker is very simple, so much simpler than systemd, right? So and the support of Docker actually for multi-kernel is very native literally from day one. So we integrated with the Docker image, so we could actually boot into the Docker image directly. So you can use any existing Docker image on Docker Hub or built by yourself. So this is a very strong advantage because there are some other cloud solution like Unikernel. They could also integrate with Docker, but in a different way. So you would need some kind of conversion. If you want to use Unikernel, however, use multi-kernel, you don't need to convert anything. And so why this works behind the scenes is actually I developed a new operating system which is dedicated to share the container root-fs image, and we just have a very minimum init process to just specifically put into the Docker's entry point. So there is no operating system in it at all. And the workflow would be very simple if you just already a Docker user, just put your Docker image and put the multi-kernel with the kernel image together with your Docker image, and you would get your service running inside the multi-kernel with the existing image. And of course, we today we have AI agent. So and every people talks about AI agent today. So and AI agent could also AI agent also need to run in the sandbox, right? So and Multikernel as an isolation actually could also provide the sandbox solution for AI agent as well. So and the advantage is actually you could get direct access to the GPU, and it could Multikernel could also offer faster snapshot compared with macro VM. And virtual machines, generally they are too heavy, and containers they are a bit leaky. So the advantage here actually is, compared with containers, we have a stronger isolation, and compared with virtual machine, especially macro virtual machine, we actually could have a faster snapshot because everything could stay in the memory compared with the existing macro VM, and also, like I mentioned, if you already have a cloud, you want to run macro VM, good luck with the necessary virtualization, and with Multikernel, you don't need to worry about that. So let's take a look at other use cases other than the cloud or the AI agent. So, and this use case actually is probably more familiar to you. So if you use Linux on a daily basis. So today, when we update the Linux kernel, we need to reboot the entire machine and shutting down all the applications. So even with the keyexec could speed this up. However, it does not eliminate the reboot process. So this is what we currently do. So what Multikernel could do better here is it could completely eliminate the reboot process in theory. in theory. So what is the theory here? So my theory is because we could actually start multiple kernels, in this case, 2 kernels in parallel. So that what does this mean? This means we already have one old kernel running, and we want to update the old kernel to the new one, right? So we could actually start the new kernel simultaneously, without shutting down the old kernel. So starting from there, we could actually gradually migrate everything from the application, the process, and the resource from the old kernel to the new kernel one by one until we could safely retire the old one. So during the entire process, there is no reboot. We don't need any reboot. And eventually, after the entire process is completed, the new kernel could take over everything. All the applications you were running before upgrade and all the hardware resources available on your machine. And that's the complete process of the kernel update process with Multikernel. So one thing I just want to mention is this is just my theory. And there are a lot of details we need to figure out because there are a lot of device driver, like hardware related issue we need to deal with if we want to completely avoid the shutdown, especially the hardware shutdown or reset. So that part is definitely challenging. So that's why I just call this a theory, because in practice we still need to deal with the hardware, which is actually much more complicated than what I described here. So, however, I do have a very ambitious goal here, and I do hope in the future with Multikernel we could avoid the reboot for the kernel update. And another use case I have is actually a little bit similar to the live kernel update is the kdump. So for the servers, for the Linux server today, pretty much I think all the servers today use kdump to capture the kernel crash. And so what we have today is, when we have the kernel panic or kernel crash, because the kdump is already there. So what does this mean? Is when the kernel panics, the kdump will take over the machine, and it will jump into the kdump kernel, and which is already which is a reboot. And during the kdump kernel, it will save the core dump of the crashed kernel. And after the core dump is saved, it will do another full reboot, boot back to the regular kernel. So as you can see from the entire process, it takes two reboots from the kernel crash until the service back to the normal. So this entire process will probably take minutes because there is a second reboot which is not with the fast key exec. And the advantage of a multi-kernel is it offers no reboot for the entire process. Like I mentioned, so we could actually start a kdump kernel along with the main kernel. So this part is a little bit similar to the kdump kernel, except the kdump kernel is running in parallel together with the main kernel. However, it will only take a very minimum resource, like probably only one CPU core and very small memory, just to keep it running and monitor the health of the main kernel. So let's say, and when the main kernel crashes, and the kdump kernel will detect this, for example, using heartbeat. And starting from there, the kdump kernel will recognize that the main kernel have been crashed. So it will start taking over the entire resource of in the machine. And and this process will take probably just a second because all the hardware resources are shared within the same node. And once this takes over, we already have a working kernel. So that means the entire process will probably just take seconds instead of minutes, and we would achieve the same result as the kdump kernel. And of course, if we want to save the core dump, we could actually also copy the core dump of the main kernel before we take over the memory. So this could also work, and we could also do this asynchronously as well. Starting over your service, meanwhile copying the kernel core dump somewhere. And to do that, actually, I started a project called KMorph. The KMorph project actually is exactly targeting the kdump and kexec use case I mentioned. So in these two use cases, they have some overlap. The overlap is they need to transform the kernel, right? So they have two kernels to transform, whether it's the crashed one to a backup one, or the old one to the new one. We have two kernels to transform, so that's why I call it kernel transformation. So and this is why I call this project KMorph. So we just need to do for the kdump use case, we just do the auto healing. So when the kernel crashes, the other kernel just automatically detects the crash of the main kernel and automatically heals the entire machine, and everything gets back in to normal, within seconds. And for the live kernel update, this is a little bit challenging. However, I do hope we could achieve the atomic resource handover, and if anything goes wrong, we could also actually roll back to the previous one without any consequences. And so this is pretty much the design of this project, and this project has just got started. So and it is still working in progress. And let's take a little bit of break and take a look at what we have so far. So I have mentioned the Multikernel and compare with the existing solutions for many for several use cases and in different dimensions. So what is the summary here? So this is I hope this chart could also give you a clear comparison of the advantage or maybe some disadvantage of Multikernel compared with the existing solution like container and virtual machine. So this is pretty much just a quick summary of what I just mentioned previous. And of course I have simplified a lot of things here, and because I just mentioned all the hardware they are participated. However, that's the ideal case. However, in lot of in practice, we do still need to share something. It's not just the hardware. Sometimes it's software, maybe the file system. We need to share as well. And the reason, for example, the hardware needs to be shared is, for example, for a server, we typically we already have so many CPU cores today, maybe hundreds, more than 200 is already kind of common for servers. However, even with so many CPU cores, the devices, the I/O devices, they are not as many as the CPU cores. So even for the servers, they probably only have a very handful, maybe just a very few number of I/O devices on the same server. So in this scenario, how could we share the device? How could we participate the hardware device? Definitely, we could not participate the whole device anymore. So in this case, actually, we do have another solution. So instead of partition the entire device, we partition the sub-resource of the hardware. For example, the network card today, pretty much they have many queues. So the idea here is instead of partitioning the entire device, we only partitioning the hardware queues. And for the network card and storage SSDs, they already have so many queues today. So that means we have much more hardware queues available than just the number of devices. And in order to partitioning the hardware queues, that means we also need to build some software solution on top of this sharing model as well. So to do that, actually, we could leverage the existing Linux kernel solution built for the networking and storage as well. For networking, we already have the XDP available, and the XDP program is pretty much targeting each of the network card queues. And for the storage, actually, we have the IOU ring. We also have the UBLK. With that, actually, we could also bind the IOU ring and the UBLK with each of the SSD queue as well. And with that, actually, we on the host kernel side, we could actually use the existing XDP and UBLK solution. And in the Spawn kernel side, we just need to build another software device inside, and they would communicate with the existing shared memory together. So with that, actually, we would still achieve the near native performance and with near with the real hardware isolation. And another thing we might need to share is the file system. And because even if we want to put multiple containers, we might not want to, build a container for each of the, build the Docker image for each of the container, right? And even some of the containers, they share some Docker image as well, and they build some, overlay layer on top of the shared Docker image. So for this idea, actually, I built something similar because the existing overlay file system does not work for Multikernel. And so the solution we built is called DEX-FS. So DEX-FS is very different with all the existing file systems because it must work for different kernel. And the different kernels, they only share the memory, and everything else is not shared. For example, they should not share the kernel data structures like the kernel inode, kernel entry, this kind of kernel structure, and they should not share the any other kernel resources like the spin lock. So this is very challenging because that means we need to build something atomic, some atomics within the memory. Fortunately, we already have some hardware atomics available in the memory, like a compare exchange provided by CPU. So pretty much we build all the atomics within the shared memory in the DEX-FS. With that, actually, multiple kernels, although they share the same memory, they could also safely write the same shared memory concurrently without any problem because we build the atomics on top of that. And because of this, actually, the host could also share the file system, for example, the Docker image with different kernel instances, and they could also not only read but also write together, and they could also share the page cache within the shared memory region as well. And with that, actually, we could achieve the real writable file system and within the shared memory. And there's another advantage actually which goes beyond multikernel. So, and this is the beautiful part of the design is, although the file system is designed for multikernel, however, it could also work beyond multikernel because there is another use case actually we need to deal with for the similar scenario, which is share the memory between different hosts, which is SCaLE. So for SCaLE 3.0, actually all the infrastructure is there because the SCaLE memory provides the coherency for the user to build the atomics we need for the DEX-FS, and with SCaLE memory pooling, actually, multiple hosts, they do need to share the same memory region, which is actually essentially the same problem what we are trying to solve for the multikernel use case. And the use case for the SCaLE is pretty much the AI training, because for AI training, we could have different CPUs. We could have the CPU cluster on different hosts, and they could actually share the same SCaLE memory pool. And if their CPU needed to coordinate within the cluster, today we could have RDMA, right? So, however, with SCaLE, we don't need RDMA. We don't need networking at all, just share the memory. And also, actually, let's say if the SCaLE cluster, they want to share some, container image or a Docker image within the cluster, we could also do it with SCaLE without any networking at all. And of course, there is another problem with kernel isolation is although we isolate kernels, but they do still need to communicate with each other. For example, when they do the resource update, so one kernel needs to release the resource, and another kernel needs to take over the resource, right? So this kind of communication is still, some shared communication channel we need to build for the multi-kernel. So for that, actually, we build some, we use the shared memory again to build the communication channel on top of the existing infrastructure called virtual socket. So virtual socket is the infrastructure used by the virtual machine today. So they communicate with this socket on the between different virtual machines on the same host. However, for multi-kernel, we need to change the underlying infrastructure because this one needs to leverage the shared memory instead of the vhost, vSOC communication channel. So that's too heavy and it's not practical for the multi-kernel use case. And with that, actually, the existing application, if they already use vSOC, actually, they almost need nothing to change, just probably one line of the change to for the multi-kernel ID compatibility. But other than that, there's nothing in the code they need to change. So it's almost 100% compatible. And let's take a look at the security model. So the security model of the multi-kernel design actually is based on the kernel enforced trust. So that means, the kernel must be trusted. So you need to trust your kernel. So this is the entire security model built for the multi-kernel, and this is actually weaker than the virtual machine. The reason why virtual machine is stronger because it uses the hardware virtualization, and the hardware virtualization is stronger than the software one, and even than the kernel enforced one. And however, there is another advantage over virtual machines. Regarding security is the attack surface because there is no complete operating system. That means we don't need. For example, system D, right? We don't need any other, initialization, dozens of service. We don't need that. We just need your own service. With that, that means the attack surface is much smaller than, the traditional operating system or the virtual machine with a complete operating system. And the kernel vulnerability is contained in a single instance. This is compared with the container. And what does this mean? And this means if you could trust your kernel, actually, multi-kernel is a very good choice for you. You control everything. You don't need to worry about running some untrusted kernel. This is a very good scenario. And cloud actually is almost perfect today because when you get a cloud, you already get a virtual machine. You don't need another virtualization, right? You already have some virtualization already, and of course, if you have your own dedicated server, they are physically secure for you. You don't need virtualization, right? There's no reason you need to buy the virtualization. And of course, all what I mentioned is pretty much focused on the kernel space. How the multi-kernel works within the kernel, and that's only part, pretty much only the half of the multi-kernel. So there is another half, as you can see, is in the user space. So the user space is actually slightly easier, actually. It's slightly easier because in the user space, all what we need is orchestration. So and because we don't have a hypervisor, that means the orchestration is much easier than QMU. So what we have here is I built another project called Curve. So this project is dedicated to orchestrate the kernel instances. You could actually put the use the existing Docker image and put it with the your kernel image, and this is the orchestration tool you would need if you want to try multi-kernel in the user space. So Curve is the project provide everything here, and it could initialize the resource, and you don't have to assign all the resource to your kernel instance for isolation, and you also it could also create the new instance and load the kernel and the Docker image into that instance, and eventually run the kernel together with your service. And it could also do a lot of other orchestration, like shutting down, completely delete everything, this kind of orchestration layer. And most importantly, it could also actually validate all the resource. Like I mentioned, the resource management is not easy. If we have different resources, we need to deal with the conflict. So this tool actually specifically designed to validate the resource when you, in the command line to allocate the resource for your service. This tool deal with everything behind the scene. So you don't need to worry about whether the memory regions they have any overlap or anything. And another advantage is because the hardware, they are not just the hardware, they have some topologies as well, right? Because today for memory we have NUMA, so NUMA have topology. Different CPUs, they might be closer to one specific NUMA node, right? So this tool also actually designed to be the topology aware, so that you don't need to worry about the topology by yourself. You don't need to worry about which CPUs are closer to this NUMA node you are using to launch this kernel. This tool will do everything behind for you. And the situation could get more complicated if it gets involved with the devices, right? The PCIe topology, this will get more and more complicated. And that's pretty much all I have. So, and I do hope you get interested in multi-kernel. So the next question is if you are interested, how do you get started? How do you, want to try? How do you try this? So this is pretty much the steps. Pretty much just 4 steps you have to get started with multi-kernel. So the first thing is, multi-kernel is not yet merged in Upstream Linux, and so however, everything is open source. So the first thing is you just need to clone the kernel, which supports the multi-kernel feature. And once you clone the kernel, you just need to build the kernel and turn on the multi-kernel feature we developed. And that's all. That's all you have. And what you have next is pretty much just like build other kernels, make install, all the same. And after your kernel is ready, the next thing, one additional thing you need to do is, I know this is still a little bit ugly, is we need an boot parameter for this, because when we start allocating the memory for the spawn kernels, that means we need to have some physically continuous memory available for allocation. However, Linux kernel has some problem to allocate, such a huge memory chunk. So that means we need to do something with this boot parameter to reserve the memory, and put this one into your bootloader like grab. And once this is ready, and once you put into the kernel with the multi-kernel support, the next thing is you need to download the Curve tool I just mentioned, for all the orchestration. and you download this tool and install this tool, and the last thing you need to do is, just use this tool to create the kernel instance. And this command line is very easy to understand, right? So you first need to initialize the resource. That means the hardware resources you want to allocate to the kernel, like a resource pool. And once that is ready, you want to create a different kernel instance, probably with different kernel binaries, all the same. So this tool does not care. And once you start, all the once you create the instance, you need to load the kernel image. You need to load the Docker image, together with the kernel service as well. And eventually, you need to kick it off. Everything will start running. So this is pretty much all you have if you just want to try the Multikernel. So I hope it's not that complicated. So what's next? So I know we have done a lot, to make Multikernel work so far. However, there are still a lot of work to do. So there are a lot of work to do actually. So the first thing is, the CPU overcommitment. And there is one advantage I didn't mention, of a virtual machine is this supports the CPU overcommitment. So that means, although you have one virtual CPU for, let's say, two different virtual machines running on the same node, they could actually share the same physical CPU. So this is, how the cloud providers make money, right? So they actually want, the CPU overcommitment. So when one virtual CPU is idle, they want, the other busy one to take over the physical CPU to better utilize the physical CPU. So this is the feature they need for their cloud customer. And another feature I mentioned, is for the AI agent, right? So the checkpoint and restore is definitely a must for the AI agent sandbox. So that means we need to support this as well. However, I do have some prototype, but not yet ready to demo for this feature. And the kernel library update, like I mentioned, is much more complicated than my theory. So we do also need a lot of work there as well. And although it already supports Docker, but it does not mean we have the complete integration or support with Kubernetes. So the next step for the existing containers orchestration is, to get it connected with Kubernetes, and so that the Kubernetes user could use the Multikernel with the existing Kubernetes command line. Excuse me. And the last feature I would like to add is the confidential computing. And this one actually is for the probably high performance computing, and they probably want the confidential computing support for the isolation. And for the virtual machine, we pretty much have the this feature ready, but for Multikernel, this is still a very open question. And of course, if you want to get involved, like I mentioned, everything is open source. So, and we don't like, although we are open source, but we don't like many other open source projects. Many other open source projects, they open everything after the design is complete. After they have to do a lot of development work. But I do the opposite. So I open everything from day one. So the reason why I want to do this is I want to invite people to collaborate with from the very early stage, so you could have the bigger impact as a contributor. You could also actually contribute to the design if you have any design feedback. So more than just some bug fix. If you feel like bug fixes are too trivial today, right, with AI, right? So we have something more challenging here, right? And of course, if you want to try this out, everything is on GitHub, on our GitHub repo. So just try. And if you see any issue, create a GitHub issue. And of course, even better, just submit a pull request. That's much better. And of course, we can build this together. And this is a quick summary, and I do hope everything you will not get confused for this long presentation, and I do hope you get the idea and the basic concept of the Multikernel. And if you have any feedback or any question, this is all the contact information I have, and you can send me some email. And all the projects are open source. It's in our GitHub directory. And also, I do have some video demos, but today I don't have time to show. So feel free to watch our video demos on YouTube. Like how to use the Docker container. That's very cool, in my opinion. And we also have a Discord community, and this QR code is for the Discord. If you are interested, feel free to join the Discord. And we also have a mailing list. Yeah, that's all I have. If you have any question, let me know. Yes. Oh, the question is, when do I finish Upstream? I think that will take a long time, because Upstream people, they have different opinions, and the code base is very large. Probably more than 50 patches, so it takes time. Yeah. Yes. Yeah. Yeah. Thank you. Thank you.
okay? This is better for our stream. Okay. They prefer us using this one, but it goes on your left here. Before we start. So. For a computer or
I do a lot of talk, but this is first time have this.
doesn't hurt. Does not hurt.
First time in SCaLE.
Down here. Okay. I'm gonna change your batteries. Let's change the battery on these. I'm sorry, what is your name?
Eating.
Uni. Did I say it right?
Good.
Uni? Philip.
Check, check.
Let me find out if there's often a room host, but I haven't seen one in this room today, so I'm gonna see if they have somebody that
I have no idea.
during questions, like, so people can use that one.
Pass it to them.
Yeah,
Good.
that's best, yeah.
Good, good,
And if
very
I can, how long is your speech? 30 minutes?
30 minutes.
30 minutes? Okay.
I'll do it very quick.
Okay, see, I'm responsible for multiple rooms, so, but I will try to check in around then, about a half hour in, and if I'll help out with Mike.
I can do it myself.
Okay, yeah, no worries then.
If you're too busy.
I might be, you never know. Here, so what I usually like to do is kind of toss the cable over in the back, and then it's usually got some back pocket, so, you can do this yourself too, if you want. But, so this part, if you need to adjust it, these are kind of flexible. You can kind of pinch that. Oh, check, check. So, put that in your back pocket, or
How do
why
I?
don't you do that?
Yeah.
Or
This
you-
side?
Or you can hook it on your belt if you want.
Hook it on my belt, man. Easy, man.
And then you don't want everybody to everything.
Okay.
And then it takes about 3 seconds.
Okay. Okay. Good.
Come on,
Good.
go ahead and say hello.
Yep. Hello. Hello. Oh, good. I think so. Yeah, I think we probably start. So people probably still stuck in lunch. And today we will talk about how RISC-V, how we push RISC-V to do the kernel upstreaming even before the chip comes back from the factory. So actually, in most of the work, the upstream work is not done by me, but actually the work, initiation is all by me because I'm the customer of the SoC, RISC-V SoC, probably the biggest customer. So I had to push that to get it done. Actually, this talk is being presented back in the Linux conference, and as well as in Boston, because I think I circle around the world and make sure everybody understand the importance of upstreaming, especially for the hardware. And most of the hardware guy doesn't understand it, and the software guy understand it, but usually really hard to push hardware guy to do anything. So even on ARM, they didn't do it perfectly. I think x86 is definitely better. And I'm going to repeat the talk, but we add a little bit more progress on our chips. So the talk is all about precision upstreaming for RISC-V forever, and then we set up the role model, and now set a very high bar for the coming SoC. So because one vendor already done it, and then most of other vendor had to follow anyway. So that is the good start. Even though it's not perfect, but it's good start. So myself is Yuning. I'm a software guy, and I used to do Java VM porting and compiler, porting and writing all the backends. And then I'm a founder of the deep computing. I found it during COVID after I sold my software startup. And then, you know, when we do compiler, usually we really arrogant. We think we're the best software in the world, software engineer in the world, and we don't even look up onto the kernel side either. So we think that we're the most prestigious software engineer, very serious. So, you know, Alan Key says one word, you be serious about software. I'm sorry that you make all your money, and now you had to lose it all on the hardware side to improve it. So, that's a story of me. So, and then I start making RISC-V laptop, and even for very slow CPU. But actually, on the hardware side, it's not very slow. If you look at all the Chromebook of ARM, similar 4-core and 8 gigahertz, you should be able to run Chromebook. So why so slow? Yeah, you know why slow? We are software guys, right? So I make the most expensive laptop back in 2023. You can look up. Everybody saying I'm a scammer. $5,000 each, and with NFT. So I know Trump is in charge. So and that's why I make sure it's worth something. And lucky enough, and the British Computer Museum have one of them. So mark the stage. And in 2004, I made a very cheap one, and it's an 8-core, much better performance, much more RAM, and a very usable one, and very cheap, all the way from 5,000 to less than 500. So, and it runs Fedora and Ubuntu. And later on, I found it out I should not waste all my money on something that cannot scale. So I just want to put something on RISC-V and let everyone use it. I just realized that 99% of money has nothing to do with RISC-V. And then one of my friends saying that, why don't you partner with framework? I said, what the hell is framework? That's back in 2005, earlier 2004. And then I got introduced to Ninav, the CEO of Framework. And then, oh my God, it's a laptop that can change motherboard. Man, I just find, okay, I can save 90% of the work. I just focus on the motherboard. So that's multiple architecture support and upgrade motherboard. Because I make every 6 months have a new SoC coming out from RISC-V. I make motherboard more than anything else. So every 6 months have a new version. So that's perfect partner. So framework needs us to promote their open hardware, not just x86, AMD or whatever. You know, they open source all the document, but no one use it. And I'm the one using it and find out all the problem. So it's perfect partners. So we redo the 4-core because I'm trying to understand how the logistic partnering works. So there's nothing to do with kernel apps. And then last year I do a very powerful one, 5-TOPS AI and 64-gig LPDDR, and then 8-core. And the only thing is not good enough without vectorized. So the memory movement performance is not good. And also it's by chiplet. That's going by the NUMA. So it's a lot of performance impact. And whoever buy that version from us for the first patch, they earn money because 64 DDR is worth more than worth the whole framework laptop. So that's a joke. So and now it's coming. So this is proper usable one, really usable. You can use daily, and with a lot of kernel support, 6.12, 6.18, and even Upstream. And then I will talk about the story Upstream. So, RISC-V versus ARM upstreaming. So I used to run Nokia's mobile phone, and this is not Linux, it's everything code source. So I see ARMs. Any chip comes out using ARM IP, we scale to KK volume, we got it in millions. It doesn't need upstream, no need, right? They make a lot of money, right? MTK, Rockchip, Allwinner, Marvell, they make, once the chip out, you have an ecosystem, you make a lot of money. But RISC-V is not. I don't know whether you guys can see it clear. RISC-V is definitely not. Just now, even we see that even the same hardware, running the same Linux, similar hardware to ARM, 4-core, 1.5 gigahertz, you cannot possibly run Chrome OS or the decent performance in Linux. You know why? Because at that time, the kernel, the toolchain, the stack of software is not optimized. So the first version of motherboard, I find it very funny, is that you have an old hardware running newer Debian is faster than the old versions. Weird, isn't it? Right? Usually, like Apple, they put more new software running the hardware is very slow. Right? So it's weird because RISC-V software is getting better and better and better. So that is why RISC-V's future is on the future software. It's not your current software. So that makes the difference. We had to upstream. If you don't upstream, you have no futures, right? Because, and I take a look example one here. So we have the first motherboard, JH710, you know, and the IP is 2018, the CPU IP, and the SoC is 2022, and then I make the motherboard is 2024. You can see actually 6 years. But upstreaming, the first upstreaming started, the pin control is February 2023. And then now the display controller and the DRAM all these are still stuck. So you can see an SoC, because the capacity of it, it takes forever to upstream. Then you start understand why ARM not doing upstreaming. Right? Any ARM SoC not doing upstreaming. Any of the mobile phone, they don't want to do Android upgrade. Right? So that is the reason. And then the East Wing one, even tougher. So, and the 50 top AI. So the IP is the year 2020, and the SoC is year 3, and then the motherboard is the last year. So, and then the CPU IP now is not even finished upstreaming because coherence is different from ARM. It's affecting all the architecture. So basically, I make the motherboard for it, make the product for it. I'm stuck with the old hardware, old software. Saying we are dead, right? Literally dead. Your kernel is old. Anything above is old, unless people backport all the features. So who's doing the backport? SoC, they move on so quick. They're not going to put effort on it, right? So I'm stuck. So I feel all the pain of it. And then, and back on, actually, and then I spoke to Greg. I said, how on earth back in x86, you know, in the old days, and how x86 does? He said, you can actually, you can get everything up before your chips out, FPGA, whatever, just buddy, do the upstreaming, even just make sure you compile, otherwise none is going to kill you, right? And doesn't run, doesn't matter, because the hardware is not there. No one can verify it's not run, right? Isn't it? So that is the difference. So, and then I say, I need to go back to x86 approach. So that's it. That's 20 years old slide. Amazed. So basically, I think most of the people doing the kernel, I think the first generation kernel guys x86, the second generation kernel guys ARM, and most of the RISC-V guys from ARM. So they forgot all the pain. Because the ARM just make business, it doesn't need futures. Right? So, and that's why I push the RISC-V is going on this. And then we managed to do something before the after the tape out, and then start doing all the. It's not exactly the same, but slightly better, but still very late. We can't do the kernel code submission before tape out, and I don't know why, but I'm not making CPU, so and it's still behind this, but still better than now. So and because no one had done it before, including me, all right, and then we do a lot of funny things, saying that okay, and ask the spaceman, do you want to do it? So I'm threatening, but actually I don't have any choice. I say, if you don't do it, I'm not going to buy your chip and make the motherboard for you. Right? I just threaten them, but they are my friends. So, and then I say, no, okay, I help you to do it. Right? Even though I don't know how to do it, right? I never do any kernel upstreaming at all. But I find a few friends just in case I need to do it. And the manager convinced the founder of it. They said, let's go. Let's do it, okay? And still don't know how to do it, right? And funny enough, because space may have a few maintainer, and they are so conscious. They say my reputation, I never done this before. I always wait for the hardware, compile, runs, and upstream. I never lie. So I never do anything before. We're really going to hurt my reputations, right? Even though Greg said, bug, kernel have bugs. Otherwise, we won't have 7.0, man. The 1.0 will be perfect. So, but anyway. So, and more fun is that we take a look how much work is, how do we inherit the previous chip. So, and Space have done 2 chips. One is K1, and now the one is K3. Actually, we find very good things. We have 60-70% of IP is inherited. So that saves a lot of work. K1 is already took 2 years upstream all the way beside except display controller, which is really awful. I had to fix it in 2 months. So, and because spaceman, I forget out K1. I had no resource for it, so I had to fix it myself. And then that is the convincing to do. So then we start. I convince somebody to do it. I just talking about the story more than technical things. I think the story is more interesting than the technical, big technical code that AI can do. So I said I write a long email with all maintainer involved, and then I send out this architecture. You know what email it comes back, and then Greg write a long email. Who the F decided this chip? Anyone spot any problem? So basically, the main problem is that they have a symmetric cluster. So in RISC-V, have two worlds. One is PRIT, RV23. One is RV23. So RV23 dictates the API, what instruction you support, work this, right? Man, now you have two clusters supporting different instructions. Oh man, go bananas! The whole thing go bananas, you know. And plus, we have finding out, you know, ARMS, the way you're doing PCIe is very slightly different from K3. Then all these things go pop up, all the hardware pop-ups. The problem pops up. So, and you know, and more, it's basically unfixable. So actually, 16 core now you will see on my hardware. Go to RISC-V booth, then take a look. It becomes 8 core, 1 cluster. So you cannot see the other a small core. So that small core is completely wasted in general computing. You can only use it for AI. And even more complex is that how I'm going to use AI? How we divert all the AI capability or whatever onto the cluster own? That makes the whole software systems complex. So that we learned that actually specific upstreaming, you can ask the software guy to help you to review the hardware. Right, and then you don't make mistake. I think, and the reason why they do it that way is because it says that, and the kernel, why you have big core or little core, this is inherit from ARM. But ARM doing very clever, same instruction, both support. No matter, it's just performance slower. But on RISC-V, it's not, for example, they were saying, why do I need a small core run hypervisor? There's no need. Right? Why a small core? You know, I just put small core, small area in order, blah, 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 blah. Yeah. And that is the hardware guy's mind. But it creates the whole software ecosystem so awfully complex. I haven't think about how do I run the AI separate just on the small core in order with AI instruction, customized instructions, and with RVV different V length. So there's very complex things. And more when we start upstreaming, because the hardware is not coming out, and then all the device tree is funny, right? Say, what name we're gonna use? Because this is called FPGA. And then they say, no, don't use FPGA because no one gonna have your FPGA. You will not be able to build anything for your FPGA. Then we had to come up with a name with the first product, but we don't really know what's the first product. And we just pick pickle, okay, whatever it means. So I was saying they pick penguin, right? Probably when I do a CPU, I will do that, you know. So a lot of things never done before. We make a lot of mistakes, but that's the purpose of how we're going to improve it, right? So we improve it with saying that, right? In the design stage, we actually on the FPGA side, we can verify all, we can upstream all the kernel code and related to CPU straight away before tape out. Once you verify on the FPGA, you all do a hypervisor, customer instruction, blah, 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 blah. All these CPU-related features you can upstream. And you separate the CPU feature out of the SoC features. So for the SoC one, you have to make very consistent. Consistent means that take a look, the kernel tree, take a look, ARM, SoC, well, IP they use flipping the same one. Then you have all the drivers someone has done for you, right? Then you are not going to be in pain for rewrite the driver and upstream it, right? So that we're saying the consistent, pick someone already done before, and the kernel stream upstream can have the driver, the support, and you don't have to do it yourself. That means that I made a SoC, our software guy have less software guy, less maintenance, every perfect, right? So that's why we said it, a consistent design. And also, I'm back to it, just commit the code, make sure it compile, minimum, right? No shame, and pick that it just need to be enough. So, and that's all actually for the experience of it. And actually, if anyone interested in helping, we still got a lot of work for this SoC to upstreaming, right? And to make it successful. And one big thing is the display controller, DRM, GPU driver, reverse engineering support, because I think everyone knows GPU driver, they will support upstream, right? So like the most predominant GPU, they saying that they only support Linux 5.1 kernel, 6.1 kernel. That's all they support, right? You're going to stuck with it. So that's same to us. The GPU is exactly the same. So we have to do research, engineer, and support. So everyone come down and take a look and help. And this is our example now. We have the hardware. We're building the 7.0 kernel and running on it. And just have serial, USB, and network, and PCIe. That's it. Just similar, very similar to x86. So that's all from me. Any questions? Thank you. And feel free to come to the RISC-V booth, take a look at all these, the things, the pain we've gone through, and be part of it. Thank you.
Huh?
It's also a pain to have it
On one ear.
stay in place.
Yeah, yeah. Especially with the facial hair, it'll rub sometimes. But anyway, I'm gonna shut it off for a second while we try to position. Talking level.
All right.
Say
Oh,
hello.
hello.
You guys here in the back? Okay, great.
Can you hear me? Thank you.
Okay, let's drop. You can do that. I don't want to get too personal with this.
Oh, yeah, sorry.
All right.
Thank you.
I'm not embarrassed, but yeah. Some of the rooms have like an assistant from the place that helps with the quick Q&A.
Yeah.
I can come if I'm not doing anything.
Uh,
About half hour in.
We can ask Jordan otherwise. Jordan, when there are questions, can you bring the mic around? Thank you. Test. Yeah, I'll wait 5 minutes. Yeah. So it's supposed to be 45, so I'll just wait in case people want to. Is this big enough for people in the back? Can you read this?
Probably
All right.
a little bit larger.
I can't see anything. Hmm? Of course. It did work last time, so it might work today. Or it might not, and we'll cut short. I mean, sorry, we just need to wait a bit more. So it's supposed to be 45, and currently it's 42. So just in case people want to join, I expect people to be a bit, not late, but right on time. So just to be sure, let's start at 45. I can feel it tilted. Feels weird. I should not move. I should be completely still. Yeah, it does. And I'll have to type at some point, and if I need to hold it, it's going to be a pain. I'm good on this side, but yeah, I've got small ears, so maybe it's same issue, you know. All right, it's 45 sharp. We can start. Okay, so hi everyone. You are here today to listen about packet filtering and BPF and a lot of other things related to network packet filtering. So I'll introduce you to a tool called bpfilter for people who don't know it. Who has no idea what this is? Well, no. Who know what this is? Oh, fuck. Yeah. Sorry. That's nice. Thank you. So we'll dive into it. Quickly, before we dive into it, so a quick introduction. So my name is Quentin. I work at Meta. I'm fighting with the microphone, right? OK. I work at Meta in the Linux user space team. I've joined. Sorry, a lot of disruption. I've joined roughly 4.5 years ago, and I've worked in the Linux user space team for 3.5. We work on open source stuff, systemd, BP. All right, bpfilter, kernel, whatever, like a lot of open source project, distros even. So I've been working on bpfilter for as long as I've been in the Linux user space team. So the plan we have today is to discuss a bit about firewall, like what kind of firewall do we have today that we could use. Then we'll discuss about bpfilter and what it is, and I guess that's the main reason you're here, hopefully, otherwise it's the wrong room. And last, we'll have a live demo, and I can show you how we use it. And fuck it, sorry. Hello? OK. And so finally, we're going to have a live demo so I can show you how it works and how you could use it. All right, so let's start with the basics. Who don't know what a firewall is? OK. You don't know? Not trying to single you out, sorry. So a firewall is a way to prevent network traffic from coming to a computer, basically, or a network. Pretty simple, you define your rules. You want to block specific IP, specific protocol, and anything that matched that rule won't go into the network. So what kind of solution do we have right now to do firewall, to do packet filtering on Linux at least? I guess everyone knows about IP tables, right? Who is using IP tables? Who is using IP tables legacy? All right. OK, so some people still. So IP tables, so when I mention IP tables here, it's IP tables legacy. It's the old IP tables. It works differently from the new IP tables. And basically, you should not use it, I guess, according to the netfilter maintainers, of course. It's the whole way of doing things. It's still alive because when a firewall works, you don't change it. And on the right hand here, you can see some synthetic benchmark. The benchmark here is just a very, very synthetic workload that you would probably not have. But it's very hard to benchmark firewall, and yes, you have a specific rule set, in which case you can compare different firewalls, and that applies to you. But having generic benchmark is quite difficult. So this one is to take with a grain of salt, right? What this benchmark does is that basically we have one rule to drop packets. We drop every traffic. And then we had more and more rules before that will be processed but don't match the traffic, right? And we try to find at which point the throughput starts to drop. So we have a 10 gig network link. And for IP tables, when you start to have 128 rules filtering on just the IP of the packet, you start having a drop in the throughput. So if it drops, you now have increased latency because it takes more time to process the packet, and you won't be able to have the same amount of traffic coming to the host. So if we don't use IP tables, we can use NF tables. Who is using NF table through IP tables? if that makes sense to you. Okay, who's using NF tables? All right, some people, okay. NF tables is a modern replacement for IP tables. When I mentioned who's using NF table through IP tables, there's a front end of IP tables that actually rely on the NF tables backend. So those are two different things. And NF tables works differently because you send to the kernel netfilter bytecode, which is then processed in a netfilter VM in the kernel. Bad benchmark here, as I said, it's very synthetic and it's not really representative of like what you could have in production. In that specific cases, NF tables will be slower than IP tables. So when we have a lot of rules filtering on the same thing, it quickly becomes slower, much faster than IP tables. What kind of options do we have otherwise? If I've got like a Linux machine running, what could I do to filter packets? There is a third option available, which is BPF. Who knows BPF here? Well, who don't know BPF? All right, quick introduction on BPF. BPF is a kernel technology that is used to do all sorts of things in the kernel, but you can basically insert any bytecode into the kernel at runtime and make it run as part of the kernel, right? So you can do packet filtering, you can do observability, you can do a lot of things like security also. Basically what it looks like is that you have a BPF-C program, which is some kind of subset of C. You compile it with Clang into BPF health file, and you load it in the kernel. When it's in the kernel, you can attach it to somewhere, let's say NIC, for example, a network card. And when a packet will cross that NIC, your program will be triggered. And you'll be able, in that case, to read the content of the packet with the headers of the packet and potentially drop or accept the traffic. That works for some hooks in the network stack, but you can have hooks on syscalls. You can have hooks basically anywhere. And in that specific example, I'm mostly focusing on like filtering packets, so having BPF programs attached in the network stack. So BPF is great. BPF is like, very interesting, very powerful. It's very, very efficient. You can filter packets before a socket buffer is allocated in the kernel. So even before the kernel reserves memory to store the packets, you can start processing it and dropping it if you need to. That's great. The downside is that you have to write C code. So I don't know about everyone, but like usually the people that write C code are not the same that create like packet filtering policies. And so if you use BPF, you would have to write that C code to go deep down into the packet and its headers and filter on what you want to filter. And you have to maintain it, and you have to deploy it. And it's much more difficult to maintain than a simple IP table rule, which would work everywhere. But it's faster, and it's way faster. So what if we could have something that is simple to use like IP tables? Just call it, it works, and it filters traffic, and something that as efficient as BPF without all the pain of maintaining C code and writing C code even. And what if that thing had like a great logo, for example, just saying, and like a great maintainer, just an example, of course. Well, you're lucky. So bpfilter is basically this. It allows you to use like some kind of DSL to define the filtering rules and use BPF in the back to generate BPF programs. Use bpfilter in the back to generate BPF programs. If we use a synthetic benchmark here, we can see the difference between IP tables, NF tables, and bpfilter. And we can see that we can have much more rules in bpfilter before we start dropping traffic. That is, again, very synthetic, and it might not apply to your use case. The speed improvement is here, but it also depends on like, what you do and how you do it, of course. You can see I don't have any benchmark for BPF, just a BPF program, because it doesn't make sense to do that in BPF directly. There are multiple ways to do it. No one would do it the same way I would do it. It's it's not really relevant for this point, but you would accept something as fast as bpfilter. So how do we use it, right? You know now about a great tool called bpfilter, but like, what do you do with it, basically? Well, that is you. You are a great blue shape, and you want to drop traffic. There is a malicious like 192.168.1.1 IP on the network. You don't want that person to come to you, right? You want to drop every packet coming from them. So what you do is that you reach out to bpfilter, and you're like, oh, okay, I want to drop traffic from that IP. And bpfilter will create the BPF program for that. So you give it the rules, it creates the BPF program, and when it has the BPF program, it will load it into the kernel and attach it to the right location. And you end up with like one command to define a filtering rule in BPF. No more C code, no more like BPF tool to load the program, no more loader, no more whatever. It's just like one CLI and it works. Well, it should work. If it doesn't, open a ticket. And so if we dive a bit more into it, it's like, what is it composed of, right? If I was giving this talk like 2 weeks ago, that would be roughly the idea. We have bpfilter, the daemon running somewhere. You have a library and a CLI. The library is for people that wants to integrate with the daemon, right? The CLI is one of the use cases. The CLI is linked to the library, and it communicates with the daemon directly. That's fine, but it was a bit cumbersome as we deploy this at Meta Arena. We want to avoid having a new daemon in production. We want to limit the overhead. So we just moved to this, which is basically no daemon, just a library, a CLI, and it works, right? So when you use bfCLI now with libbpfilter, you don't have any daemon, and you give it the command, and it's going to create the BPF program, attach it, and make it live on your system. What it does is that basically there are 3 different steps. The first one is the DSL, which we will see a bit later. It's quite similar. If you're used to IP tables or an F table, it's not going to be surprising to you. When we have the DSL, we convert that to an internal representation of the rule set. From that internal representation, internal data, we create the BPF bytecode, right? It's very similar to like assembly code. We'll see what it looks like later. But it's like basically assembly code. And so what we do is that we allocate a huge buffer of memory and rewrite the instruction, the assembly instruction, one after the other into that buffer. And so every program generated by bpfilter looks roughly like this. What we have is that, first of all, there is a prologue. We set up some kind of internal data before we process the packet. Every program we have will be called once for every packet. So if you attach a program to the NIC directly, every packet going through the NIC will be called with the program that's attached to the NIC, right? What this means is that the runtime of the program, the internal data and storage you have will disappear once the program terminates. So it has one run, it does what it has to do, and then everything disappears. And it has another run with another packets, and everything's roughly like temporary. That's how BPF work. And so we have that command prologue, which helps us setting up some internal settings for this run of the program. Then, because we support different BPF program types, we need to find a way to have some generic data we can work on. BPF can be attached to various hooks, various locations in the kernel. And we can attach to XDP, which is very early in the network stack. We can attach to TC. We can attach to a C group to filter traffic coming to a specific C group. Or we can even attach to the IP tables and NF table hooks. But all these programs are different from BPF point of view. They expect different arguments. They work differently. They return different values. And bpfilter must be able to support all of them. So to ensure we do that properly, we have that red part here, which is a way for bpfilter to like set up the runtime context of the program for that specific packet And so from there on, we know that every field is properly set. We know that we have a field in the runtime context with like, what's the protocol on layer 2 header? What's the protocol on layer 4? What's the packet size? Because depending on the program, we don't compute the packet size the same way. And once we have that setup done, we can process the rule the same way for every program we generate. And the rule is pretty simple, right? We have a way to match the packet, and we have an action to take. We have, for example, we'll have a look if the IPv4 source address 192.168.1.1, if it's that, all right, we can drop the packet. If it's not, it doesn't match, we jump to the next rule. And so when that's done, so we have all the rules, one after the other in BPF bytecode. It's like unrolled. And if we have no rule that matches the packet, then we'll have a default action, which is like a chain policy in IP tables or NF table. Like by default, we're going to accept all the traffic, but we can like drop stuff with the rules in the middle. And that's basically it. You can see at the bottom we have custom functions. That's a way for BPF programs to define pieces of code you can recall, like you can jump to and come back from. It's basically functions. And we use that a lot to avoid code duplication, bytecode duplication, which would grow the program substantially. There are pieces of code we reuse a lot, like updating a rule counter, for example. Well, we have one coroutine for that, which we reuse a lot. And similarly, there is some stuff that we don't want to write the bytecode for. I guess some of you already wrote assembly before. It's a pain. It's a pain to debug. We don't want to do that for some features that are not used a lot, and that might be very fragile. Processing the IPv6 extension headers, for example, the IPv6 options, that's a pain. Most of the traffic won't have any extension header anyway, so we might as well have a function for that and just reuse it. And this type of function, we do write that in C, we compile it with Clang, and we extract the bytecode and we copy-paste it basically in the final BPF program. That is very useful to us. We save time, and it's more reliable, especially for complex assembly. The downside is that you call a function from BPF, so you have some overhead. So we do that for non-critical features, or the features, the code that we reuse a lot, because you have the overhead of creating a stack frame and jumping later in the program and coming back then. All right. Is there any questions so far? Am I clear? Is it like a lot to digest at once? I see some. Okay, I can get it. We'll have a demo right now, so hopefully it's going to make more sense to you. So, demo time. It should not fail, honestly. We should be fine on this. Yeah, it's too late now, I guess. I just need to have my display here too, so I can actually see what I type. All right, so you should see that. All right, that's great. So I need to find a way to speak and type at the same time. Hello? Yep. It works? Yep. Great. Sorry. Okay, it works. I'll try not to move too much. So before we start, that's the documentation for bpfilter. Can you see that? Yes. Okay, I can't turn my head, so I'll rely on you on this one. That's the documentation, and we can see how you use bfCLI, the command line tool, and we can see how you define rules and rule sets. So that's what we'll do right now. So before anything, let me be sure I have everything I need. The setup is pretty simple. I have a VM on my Mac. I connect to the VM through SSH. And the ping you can see here is my host pinging my guest, so my host pinging my VM. We'll play with that a bit in a minute. Let's ensure I don't have any leftover chain here. All right. Let's have a look at this. Can you see this? Yep. All right. So what you see here is how we define what's called a chain. People using IP tables and F tables roughly know what I mean by chain. It's like it's a set of rules that you apply somewhere in the filtering path, in the networking path. In this case, it's pretty straightforward. Chain is just a keyword. Demo is the name of the chain. I called it demo, right? bfhook XDP is the location we will filter packet from. So that's XDP. It means we attached that chain to your NIC, basically. By the time this chain is executed, there is no socket buffer allocated yet. It's very, very early in the networking path of the kernel. I give it the interface to filter on, so where the program should be attached to. That's interface 2, that's the main interface on my machine, on my VM. And the default action, which is accepting any packet. No. So when I'm here, what I want to... I have a lot of trouble like speaking and typing at the same time, so we'll have some quiet times. So when I'm here, what I do, that I do rule set from a file, and that file is 1.bf. All right, no error, that's fine. Now what I do is I'll try to print the rule set. When I say rule set, it means like all the chains, all the filtering programs defined on the machine. So printing all the chains, we can see I've got just one chain, which is the one I've just defined. And we have counters. So by default, the chains will have a counter of number of packets and bytes that goes through the chain. We can see there is traffic coming. We can see there are no errors, so that's great. Good to me. And that's not much interesting, to be honest. It's just something somewhere like watching packets going through. What might be more interesting is that if you use the usual, like the standard BPF tool binary, we can see that if I check the network programs, I have one program, ID 8C, on interface 2. You can not trust me on this one, but I tell you that's my program. It's not coming from anywhere else. Let's build some confidence, right? What can I do next? I can use, oh yeah, I should show you the bytecode itself. So using this very verbose command from BPF tool, I can dump the actual bytecode. So this is BPF bytecode. It's like assembly. Anyone who has seen assembly at some point wouldn't be surprised by what happened here. So this is the actual BPF bytecode. It's what bpfilter writes into that memory buffer loaded into the kernel. That is the very, very beginning of the program. We store the arguments in some kind of stack space. We can see the registers being used. BPF has 10 registers from R0 to R9, and there is R10, which is used to store the frame pointer. I won't go into too much details, but like it's basically BPF assembly, right? This is a specific function call. BPF has access to some kernel functions, and this is one of them. This is part of the kernel sources, so we can actually use kernel functions from BPF. And this is another function call, which doesn't look good. It doesn't have like a pretty name. This is one of the functions defined inside the program itself. So it's at the very end, and what we do here is that we jump into that function somewhere in the program, and when that function is done, we just come back to instruction 22 in that case. And that will be done for assembly code. We won't watch assembly anymore. You're safe. Now, let's have a look at the BPF file system. Who know what BPF file system is? Who don't know then? Right. BPFFS is a virtual file system in the kernel. Basically, when bfCLI creates a BPF program, it's going to load it into the kernel. When it's loaded, what we have is a file descriptor to that program, right? The issue is file descriptors for BPF objects acts like a reference counter. If we close the last file descriptor, the program is removed. And I mean, we don't want that, right? We don't want the program to disappear when we close bfCLI because it's just closed by itself at some point. So the solution is to keep a file descriptor open somewhere, roughly. And to do that, what we have is the BPF file system, which is a file system where we can pin BPF objects into. So what bpfilter does is that it will create and load the BPF program, and then it's going to pin that program into the BPF file system. So when bfCLI returns, the program still exists. And we can see here what bpfilter has defined as BPF objects for that simple chain here. bfprog is obviously the program, right? So it's the bytecode we just saw. We can see a bflink, which is a way for bpfilter to attach a program to a hook. You can do it without the link, but the link allows you to perform like in-place atomic updates of a program. So bpfilter can, when you update a chain, it's going to create the new bytecode, load it, and atomically replace the old one. So that way, you don't have any downtime in traffic filtering, as you would expect from any firewall, basically. What do we have? BF context is the content in the rule sets in the program, but in bpfilter format, so we can then reload it and like update it if we need to. And then we have two maps. I told you just before, the context in the BPF program at the runtime will disappear when the program returns, right? So we need a way to store data after the program ends. And that's what BPF maps are for. So a BPF map is like a storage area that you can use in your BPF program that will persist after the program ends. And we have two maps. We have a maps for the debug strings. So when there is some failure from a kernel function, for example, we log something. Obviously, we never log anything because nothing fails ever, right? Especially not on bpfilter side, right? And we have a counters map. The counters map is a way to store how many packets and bytes have been processed by a specific rule. And that's basically it. So now let's do something a bit more interesting. I have another chain here. Different name, different hook. We hook on TC here. TC is a bit after XDP. So at this point, we have a socket buffer. So we have kernel memory allocated. It doesn't change much on what bpfilter can do. It's just that it requires more processing on the kernel side. At this point, there are more resources that have been used to process this packet. Same option, we attach to interface index number 2. And we can see 3 different rules. The first one is like catching TCP traffic on port 22. We count the traffic with the counter action, and we accept it. Same for UDP. And the third one is we check the layer 4 protocol in the packet. If it's ICMP, we log the packet. We actually log the link header, which is L2, the internet header, L3, and the transport header on L4. And then we count the packet and we drop it. So right now, I can ping my VM. And if everything works as expected, when I load this rule set, we shouldn't be able to ping my VM, right? So let's do that. So this time, we won't use rule set command. We'll use chain set. The difference here is that it did not remove the previous chain. So when you do rule set, you apply at the rule set level. So you basically override anything that could be running on your system, bpfilter-wise. When you do chain set, you operate at the chain level. So in this case, we define a new chain. If there was a chain with the same name defined already, we would have replaced it. But there is no chain with the same name, so we just added a new one, and so we have 2 chains right now. And what we can see here is that we don't really care about the TCP and UDP rules. What we care about is the ICMP drop. So we can see that we already matched to 44 packets. So it's been 44 seconds since I've inserted the rule, and 4,000 bytes, and growing. And obviously, on the other end, we can't ping the VM anymore. That's fine, it works. Let's have a look at the logs now. So I've got my, my action. The log here is an action. And we would like to have a look at the logs collected. Oh, Jordan?
So,
I can repeat the question if.
yeah, just repeat. If there was already a rule that said accept, does it, I mean, as soon as you added the chain after the accept, I thought he's going to show us that it's still working because you've got to pull the accept out. Does it match a rule and stop, or does it match a rule and continue on until it finds the most restrictive? Like, what's the...
For a single chain, when it reaches what's called a terminal verdict, it stops. So accept is terminal. When there is a rule matching a packet with the accept verdict, it's going to stop. It behaves like IP tables, basically. If one of the rules matches the packet, you apply the action of the rule, and then it's done. So when we have traffic, when we catch traffic on port 22 TCP, the first rule here, the action is accept. So we accept the packet, and the BPF program stops. So we won't do any more filtering. There is a way to do more filtering, and it's with the continue keyword, in which case you would jump on the next rule. Does it answer your question? It doesn't.
No. Because as soon as you, I mean, your first one said, your first rule, the first one, the 1.f or whatever it was, you said we're going to accept everything, right?
Sorry?
Yeah, the one that was XDP, whatever it was.
Okay, so the question is, so this thing says we accept everything, right? Okay, it does. But it accepts everything at that hook. And then the packets will continue in the network path. If you use IP tables on a pre-routing hook, for example, you can have rules there, and you can have actions on the packets. If the rule accepts the packet will continue its flow in the network path, right? And at some point, it's going to reach the local in or forward hook, where you can do more filtering. And you can drop the packet at this point. Any other question?
Just to be clear, it does hit the demo chain passes it on, and then it goes through the monitor chain, and in the monitor chain it gets dropped, correct?
Yes. So I'll repeat that. So what happened here is that the XDP hook is the first hook in the kernel, in the network path. So the packet will go through the XDP hook and the chain. At this point, we see the packet, we accept it. And then it will continue its path in the network stack and reach the TC hook. And so again, at the TC hook, the program will run and filter the packets. At this point, if it matches the ICMP drop rule, when, well, the packet is dropped and the packets won't continue in the network stack. It's very similar to the behavior of IP tables and F table. Now, let's have a look at the logs. So bpftrace chain logs, the name of the chain, which is monitor. And we can see traffic, yeah. Unsurprisingly, that's just ICMP, because we only log ICMP traffic. We ask for L2, L3, L4, so link, internet, and transport layers. So we can see some details about those protocols. We can see that it's rule number 2, how many bytes, and it dropped the packet. That's about it on this one. Let's do something even more interesting, right? let's say I've got a game server running on my machine. My host IP is like the 10.2.11.55.2. So I want to allow myself to connect on my Minecraft server. I want to drop anything else in the network. I don't want anyone to reach out to my precious Minecraft world, right? So I do that. And this time we will override everything. So we'll do rule set from a file which is 3.bf. All right. And it's up and running. I can still access the VM, so it works. Otherwise, I would be blocked, which is actually very, very common. When you work on network, basically, like firewall in that case, but something that happens often is that you try the new features, right? And I often try new features and ensure that the new matcher works and I can filter traffic. The thing is, on a VM, there isn't much traffic coming. Like, there is nothing coming really except you working on the VM. So a common case is like to catch traffic on port 22. But the thing is, usually, like when you catch traffic and you play with traffic on port 22, well, you quickly drop traffic on port 22 and you need to reboot the VM, right? So be careful with that. And I learned very quickly that the servers we have at Meta are very, very slow to reboot when you can't access them. Not fun, having like a 5-minute downtime in the middle of the day. So I've got my traffic here, my rules, sorry. It's great. I can allow my traffic to go through. But I might want to do a LAN party. I want to invite a few friends at home. So I would have to let them go through. I can do that, of course. I can do more rules. So I will assign them an IP and then go with bpfilter to allow those specific rules into my firewall. So I've got 3 friends coming, and we can all play together. That's great. Inserting the rule set, checking out. OK, I've got rules for everyone, so my friend can reach out to my Minecraft server. We can play together. That's nice. But the thing is, eventually, I might have more friends coming, right? And we could play together. It would be great to have like a huge LAN party, right? But there is an issue here. I should not welcome more than 1,000 friends to play with me, which might be an issue for my wife if I've got 1,000 people joining me at home. But like, let's imagine we have a big, big LAN party somewhere, and I want like a lot of people to reach out to my Minecraft server. What happens if I have 1,000 rules, 1,000 people coming, or like 2,000 or 5,000? The more people I will allow through my firewall, the slower the throughput will be, and the higher the latency will be. And that's going to be an issue for everyone. It's not going to be fun for a long time. So what we can do instead is being like a bit smarter with the rule sets. Who know the sets in NF tables or IP sets? So basically, that is a very simple concept. It's like you have a bag of IPs, and you filter on the bag of IPs, on all the IPs at once with one rule, instead of having one rule for 1,000 different IPs. So that's what we do here. What we define here in bpfilter is like we define the key. So we're going to filter on the IP4 source address. And we want to check if the address is in one of those addresses here. So we can do that with just one rule. So instead of having 1,000 rules to filter 1,000 different IPs, we have one rule that filters on 1,000 IPs. 1,000 is a bit light. We have tested all the way to 5 million of IPs in that set. And it filters traffic as fast as like one rule for one IP. That's the huge benefit of it. And so I've defined my key, which is IP4.source address, and I've defined the elements in the set. I could as well do a composite key. So I would like to filter on the IPv4 source address, but also the TCP destination port. And I could add, oh, I also want to filter on the, doesn't make sense, but like TCP.source port. And then I just have to add the missing elements from the key, and I can go on and like create more complex sets. And bpfilter will create the bytecode that will create that key and look up the key in the set at runtime. For now, we'll just filter on one set. I'll reuse the command and load that rule set. I'll print the rule set. And we can see that the rule set has been updated, and then we filter on a set now. And we can update the set, insert new IPs, and still have one rule. So the processing time is exactly the same as if I had one IP to filter on. It's exactly the same thing. We can also do something like that. It's slightly different, but that is a way to define a set that you can reuse in different rules. So it's a named set. You tell it, OK, I define a set. It has this name. This is the key. This is the content. And then you reuse that set in the rule here. We can see on this line. The benefit of having a named set. Did I insert it? Not yet. So it's working now. The benefit of having a named set like this is that we can call bfCLI to just update that set instead of updating the whole chain and modifying the source file and whatever. So I do update set. The name is LAN. The set name is my friends. And then I want to add. I could also do remove, but in that case, it's not relevant. And I want to have 10 to 11, 55, 10. And we have it in the set. And now we will filter on 5 different IPs. And I could have many, many, many more IPs in that set if needed. And that is it for the demonstration. And the talk also. So, wait, no, wait a minute. Sorry. It's it-ish, right? I've got one last slide, which is, if you want more information about bpfilter, we have a website, which is bpfilter.io. We have, obviously, a GitHub, which you can have a look at when the GitHub infra is up and running, which is sometimes. Don't say that. Don't repeat. Don't quote me on that, please. We have RPM packages, which are not really up to date. We had a lot of changes lately as we are deploying into production at Meta. And I need to update the RPM packages with the latest changes, which is no daemon. You can have a look at the source code. You can open issues if you have issues. You can reach out if you have any question. You can reach out if you want like a ticket to work on. We have tickets for issues on GitHub open for beginners. If you want to have a look, feel free to check it out. If you want to have some help into like jumping on the bpfilter code, you can reach out. I'm always available. Or if you have any question, reach out. And this time, I'm done. Questions?
So for things like Docker and other stuff, they obviously already go in and create NF table rules and stuff like that. Can you run bpfilter at the same time and not have issues? Obviously, you have more than one firewall system is not great, but are you able to use both at the same time?
Yeah. It's not going to attach to the same thing anyway. You're not going to override the IP table rule sets using bpfilter, even if you attach to the same hook. But you might mess up traffic anyway, because you would have 2 ways of filtering traffic. Otherwise, it's fine.
Which one would take priority in that situation then?
That is a good question. So if you attach to XDP, bpfilter would run first. If you attach to TC, same thing. If you attach to one of the IP tables or NF table hooks, that is a very good question. And having a look at the kernel source code would answer this. I don't know out of my memory, sorry.
A little bit of a curveball here. How do you deploy this, like in SCaLE? Like, do you just like send these files to the host and then just reload it?
How do you deploy this?
Yeah, exactly. Like how do you make this like available in production? Yeah, the rule sets, right?
Yeah, you send the rule. You give it the rule sets.
So you send the files, kind of chef or whatever.
Yeah. For example, and the rule set can stay on the host, and you can have like a system action at the very beginning, at the very early boot of the system that will call bpftrace and apply the rule set. It's roughly like what you would do with iptable save and iptable whatever restore.
Do you have mechanism to check that the configuration doesn't drift? That whatever you're running because of the. Oh, I thought you had a question. Okay, so yeah, so like how do you make sure that the things that you're sending to like the configuration that you're trying to configure doesn't drift from what you want to write?
So basically, what if someone modifies the rule sets?
Yeah, exactly. Like someone modify the rule setting, whatever server you have, you send it through Chef to the host, but that thing never loads, right? Like do you have a way to check those things?
You can read the rule set and check what's inside. Mm-hmm. Right now, what you write in the rule set in the text file is almost exactly what you read from rule set get when you call bpftrace. So you could compare that. The only difference is the counter's value. But we have plans to like allow you to specify initial counter value, in which case you could just compare it. But I think that's a problem that's outside of bpfilter itself. It's more like a configuration management problem.
Follow-up question. When deploying at SCaLE, obviously I'm assuming that there will be different kernel roles that will have different rule sets applied to them.
Yeah.
How do you think, like, is there a central management system where you configure once and then push the configuration out?
No, I think that's outside of the scope of the tool itself, right? It's mostly configuration management issue. As far as bpfilter is concerned, only the current machine exists. And traffic coming, obviously. But like, it's not aware of like a whole cluster, infra, whatever. That is a different issue that should be resolved by different tools.
Okay, so.
Thank you. Is there planned for or an existing capability to interface with network queues for IDS sensors?
For
IDS sensors or IPF, intrusion protection systems and such?
Not yet. What we've done, the furthest we've been into like whole system, other tools integration is for some time I had a patch for IP tables to use bpfilter, the library, which is not available anymore because it wasn't maintained. And I think now with like a good AI, you could like translate from IP tables to bpfilter if you need to. And otherwise, what we do at Meta sometimes, like we want to inject latency into some traffic. And what bpfilter does is that it marks the packet, and then we have TC disk catching that mark, the traffic with that mark, and injecting latency for testing. That's a bit as far as we go so far, because we don't have much use case.
Thank you.
Hey, two quick questions. First, what were you using for your shell history?
It's...
Is that A2N?
What is it? No, I don't know.
Okay.
It's something, so it's my history is piped to FDF.
Oh, okay, great. And then The
and it looks quite nice, right?
Yeah, yeah. And then the second one is, I think, similar to his question. How does this interact with other BPF programs like bpftrace or Cilium? You know, can I load these rules before or after those?
So with bpftrace, it shouldn't be an issue. I'm pretty sure bpftrace can't attach to network stuff.
Oh,
Can
okay.
it, Jordan?
I don't know.
No, it can't. Okay. Jordan is working on bpftrace. So I'm just double checking I'm not saying dumb things. And so if you have other BPF programs running, you're responsible for what could happen, right? There is nothing preventing you from attaching two different TC chain. You can even do that with bpfilter. You can have an existing TC program and attach another one with bpfilter. No issue. How the kernel behaves when you do that is that the first program runs first, and then the second program. And if the first program drops or accepts the packet, the second one won't be executed. XDP, well, you can't, because you can only have one program at a time. For cgroup, it's fucked up. Sorry.
Is that a technical term?
For cgroup, basically what it does is that if you have two cgroup program filtering packets, it's going to run both of them. If one of them drop the packet will be dropped. But if the first one drops the packet, the second one will be run anyway, and the packet will be dropped. Doesn't make sense. I'm not responsible for it. It's weird. Anyway, but yeah, you're responsible for handling that part because we're not aware. We can't be aware of the other tool using the BPF hooks, unfortunately.
What kind of traffic logging is available? Is it just the human readable, or is there a machine readable?
What kind of? Sorry.
Traffic logging?
So logging is pretty straightforward. We have a C structure that we log into a ring buffer, and you are free to use the API to get the file descriptor of the ring buffer, and you have the binary data. What bfCLI does is that it reads the binary data, which is basically the packet headers that you request, and it prints them. And it pretty-print them. But you could very well read from the file descriptor and print what you want.
Thank you.
Hello. Could you remind me where your bpfilter places those eBPF hooks, which layer? Is that a NIC level, or is it in the kernel?
So we support multiple hooks. So we can attach to XDP, which is at the NIC, before the socket buffer is allocated. We can attach to TC ingress egress. So at the driver level, after SKB allocation on ingress and egress path, we can have C group socket buffer, C group SKB. So every packet coming to a C group on ingress or egress. We have the BPF net filter hooks. So it's pre-routing, post-routing, forward, local in, local out. And that's about it. And I've got someone working with me working on cgroup sock address, which is filtering at the socket level. So instead of having every packet going through, you would have the send message or connect or bind request directly. Which contains some network data like an IP, destination IP, source IP, the port, that kind of thing. And you could filter there directly. But it's not there yet, the sock address.
Gotcha. Thank you.
I have a follow-up question.
Yep.
What is the benefit of attaching to later in the networking pipeline if you can do filtering earlier, on the NIC? Do you have more bpfilter features available to you when you have kernel memory allocated?
Yeah, you have sometimes more features. You can't mark the packet if you don't have a socket buffer. This is a socket buffer field, so XDP can't do that. You can't BPF XDP can do redirects. Not all of them can do. There is something about sending the traffic to a different NIC on egress. We have that recently because we want to test lost traffic. And so we use bpfilter for that. The issue we had is that if we drop the packet on egress to simulate network issue, the kernel will be aware that the packet has been dropped, and the kernel won't retransmit the packet. So the kernel is smart. And that's not good for us. We want to have the overhead of resending packets over and over. And so what we do is that we redirect, instead of dropping, we redirect the packet to the loopback interface. And the kernel see the packet as sent, but no answer received, so the packet is missed, and it retransmits. So basically, the features you can use depends on the hook you attach to. We good? Any last question?
Going once, going twice. Oh, one more.
Given that both bpfilter and nftables encode their rules as bytecode and run them in a VM in the kernel, why is it that bpfilter is so much more performant than nftables?
bpfilter, BPF is not a VM. BPF sounds like a VM, it looks like a VM, it behaves like a VM, it's not a VM. Well, it's for some definition of VM. So netfilter has actual bytecode that is run in a VM in the kernel. BPF bytecode is cheated into machine code at load time. And when it runs as machine code, at least on x86 and ARM. I don't know about the other architectures, but and so it's like you would write the C code and compile it as part of the kernel. And that's the main reason. And one other thing, which we don't see here because I don't have it, but like there was an example. Oh no, we can see it actually. So we can see that the baseline, when there is just one rule between IP tables, NF tables, and bpfilter, like we already have that small difference in throughput. The reason here is that we filter earlier if we attach to XTP or TC with bpfilter than if we filter on the first net filter hook. So we can have some performance increase at this location too. And so the rest of it is just, well, we have machine code and they have bytecode, and so it's faster.
Thanks. Thanks.
Okay, anybody else? Oh, another one. All right. Yeah.
Yeah, go for it.
Hey, thanks for the great talk. Can you say a word on how you generate the BPF? As in, do you generate C code and then compile that with Clang, or do you generate the VM, or is there anything reusable for other tools, or what's the
So
approach?
we use a big buffer of memory we allocate with malloc, and we write the struct BPF instruction into it, one after the other.
Okay, so you go from your DSL directly to the
Yeah,
VM.
we are the compiler.
Yeah.
That's the idea. So it's sometimes a pain, but it's very fun. I suggest you can try it. And it's like you have full control over what you do, and it's actually very great because sometimes we want to cut corners, which is very hard to do with Clang because you go from C code and you don't really control what it does. And it's actually very simple. It's not that complex at all. Yeah. What we do is not extremely complex, so we can do it ourselves. There are some cases where we have BPFC source files into the repo for some features that are hard to write in assembly directly and fragile and not much used. So we write BPFC, which we compile into Clang, and we just steal the bytecode and put it into the final program.
Got it. Do you think there's scope for a project that makes generation of BPF code simpler to be used across multiple projects, or you think there's no point in doing that? As in, like, sharing a compiler between several projects in the future, do you think that would make sense?
It seems very close to what we discussed at some point, Jordan. So Jordan was on bpftrace. bpftrace goes from a DSL to a BPF program. They do it using LLVM, and they have much more, like it's much wider scope than what we have in bpfilter. And at some point, we actually discussed about like having some like a common backend, and so we could create many other tools with a DSL and convert it into BPF bytecode. I think that idea stopped quickly when we discussed with some maintainers, which was apparently not that great of an idea. Yep. So, I mean, if there is a use case for it, sure, we thought there was. Apparently, no, not everyone agrees on this. So, that's not a great answer, but that's as much as I have.
Anyone else? Okay. Thank you.
Thanks a lot.
ID mapping yet.
How long is your thing? An hour or 45?
15 minutes.
Okay, that's plenty of battery. You can tell these guys a quick story. Go ahead.
1, 2, 3. 1, 2, 3.
Can you hear them in the back there?
1, 2, 3.
Sir, anybody? So?
Hello, hello.
It's coming through. Speak louder.
Yeah, okay. That's better? Cool. Thank you.
That's perfect, actually. Yeah, that's great.
Okay.
Okay. So, and I like to throw it over my shoulder and throw it in my back pocket, but it really depends on, like, so the cable isn't in your arm area.
So, like that.
Like, yeah, and put that around your, yeah. Here, let me help you. Jump through there slowly.
Cool.
Yeah.
Okay.
Cool. Okay. If it's moving around a lot on you, you can always put a little
Tape.
like, tape behind the ear.
Okay.
Or something. You want to do that? Or?
No, I think it's good.
If it's comfortable,
Yeah.
I give a shit.
Yeah, it's comfortable.
Drives me crazy more than
Yeah.
It just depends. Yeah.
Yep.
But there was a girl, a couple, like yesterday, she was just okay, or just like, it was moving around.
Yeah, it's all a mess. Yep.
I'll let you.
Yeah.
Focus.
Cool. Thank you.
I'd be happy to do it. Quick question. Sure. Yeah, sure. Okay. Yeah. So you can introduce. Oh, you want to introduce? No, you don't have to. Just for like, but for after when you have questions, if you want to just.
Sure, hop up and grab the mic.
Grab the mic.
Yeah.
Hello, hello.
Thank you.
Leave them on.
Cool. Hi, everyone. Thank you for coming to this talk. My name is Andres Beltran. I work for the Linux Systems Group at Microsoft. My team works on the Azure Boost project, which is basically a system offered by Microsoft internally that offloads virtualization processes to dedicated hardware, including SoCs or SOCs on a chip. We use Linux extensively for this, and obviously we run systemd as our service manager in this custom distro we run for Azure Boost. And that's what the talk is going to be about today. It's some work I've done with the Upstream systemd community to modernize and enhance the capabilities of local storage management for systemd services. So this is going to be the agenda for this talk. I'm going to start with a brief systemd overview of what it is. And I'm going to discuss some important concepts that are going to be relevant for this talk, including the one of dynamic users in systemd, and then local storage directories. The second part of the presentation is going to be ID map mounts, some use cases for this, how we did the integration of ID mapping for systemd storage directories, the internal mechanism for ID map mounts, and a quick demo. And then I finalize with the other part of the presentation, which is about these quotas. I'll give some background about it. Again, the integration of these quotas for systemd storage directories, the mechanism used for this, and then another demo for this section. OK, so let's get started. So in general terms, what is systemd? As you may already be familiar with it, it's the init system and service manager used by pretty much all major Linux distributions right now, including Fedora, CentOS, Red Hat, Ubuntu, you name it, right? Systemd runs as the PID1, which is the first process that starts after boot. And then it's in charge of starting and monitoring all other user space services and managing their dependencies as well. It provides very aggressive parallelization capabilities upon boot, because as you can imagine, we want to start everything as soon as possible during early boot. It also provides on-demand activation services, socket-based activation services as well. It has some capabilities to provide network configuration during boot as well. And then it manages resource control for services based on Linux C groups or control groups. For all of this, it exposes different configuration files. The most common one is the .service one, which is where you define all the configurations for your system service. There are other units as well, the .socket to define or to configure your sockets, timer units, which are often associated with the services to determine a cadence in which the service runs, the mount units and targets, which basically group together different services. There are two primary tools in systemd that will be relevant. The first one is systemctl, which allows to control the start, restart, stop of different services. It also allows you to check the status of your system service. And then journalctl, which provides all the logs from the Linux kernel and systemd's native units and any other service register with systemd as well. So it's the centralized logging provided by systemd. OK, so as seen before, systemd offers many capabilities. I'm going to focus just on a couple ones that will be relevant for this talk. The first important concept is the one of dynamic users with systemd. So dynamic users can be enabled by setting a particular directive called dynamic user. And you can set it equal to 1 or yes to enable it. So when you do that in a service file, systemd is going to allocate a pair of a Unix user and group ID when the service starts. And then it's going to release it or release this pair of group user ID when the service terminates. The way systemd goes about this is by picking the first available UID from a predefined range that is, I think, hard-coded in systemd. This is from 61.184 to 65.519. And then an important part here is that systemd does not directly touch the etc password file or the libs in disk. Instead, it uses a glibc module called NSS systemd, which writes the new UID and GID to the system user database and group database, respectively. The benefit of having a service with dynamic user is that a system in this way can run a privileged separate service that leaves no artifact in the system. So systemd is going to allocate the UID when the service starts, and then it's going to release the UID when it terminates in a safe and secure way for later use, specifically taking care of UID recycling, which I'll talk a bit more in the next slide. And the other benefit is that systemd doesn't need to pre-allocate UIDs since they can be allocated dynamically, so this does not drain the available UID pool any longer than necessary. Okay, so the second important capability will be the one of systemd storage directories. These directories help define where the systemd service stores their data. So as you can see on the table on the right, there are 4 types of storage directories. The first 3 are persistent storage directories, including the state directory, cache, and logs. And the last one is for temp-effaced files. So the runtime directory, that's where you put any data that is temporary and that will be cleaned up after the service terminates. So the first 3 are more interesting since, as I mentioned, they are persistent. So this means that the data will survive from one invocation of the service to the next. And systemd creates namespace bind mounts for these directories. So this means that you will have those paths in the middle column in the host namespace. And then systemd is going to create a bind mount when the service starts. And it's going to show in the unit's mount namespace with the same paths. Now, an important consideration here is the sticky file ownership problem when you combine it with dynamic users, as we saw before. This basically means that in the scenario where you have a systemd service and this service creates a persistent file, then in Linux, obviously, the ownership for that file is sticky, meaning that once the file is created, unless you do a chown explicitly, the owner of the file is going to be the same, right? So you can imagine this could be a problem when a system service starts, creates a file, then it terminates. And then if the service is using dynamic users, then in theory, the UID could be recycled. And a second service, starting later, could grab the same UID. And what that's going to do is it's going to have access to the files and the data that the previous service created, which obviously is not what we want and could be a pretty bad security vulnerability. So to take care of that, what systemd does, it creates these boundary directories, which are the ones on the last column in the table. These are basically host directories that are made inaccessible to any other user that is not root. So in this case, any unprivileged user is not going to have access directly to the data stored in those private directories. Effectively, this ensures that the access cannot be gained through the dynamic UID recycling, as I explained before. So the talk is going to focus on 2 important features I have added to enhance these storage directories. The first one is the integration of ID mapping for them, and the second one is the application of these quotas for the persistent storage directories. So that's what I'm going to be talking about next. OK, so I'm going to start with ID map mounts. So for a long time, it has usually sufficed to track a single owner and group for files and directories in Linux. But there's been an increasing number of use cases for making the file ownership relative to the environment the process is running in. So in many of these instances, the UIDs and GIDs for the files do not necessarily match the ones do not match the current user of those files. So for example, in containers, that could be the case, where you have a container running with an unprivileged UID, and you might want to have different UIDs for those files. So in these cases, the ID map mounts provide a solution for that problem without necessarily changing the files on disk. In addition, file ID mapping can be useful basically for file sharing within within the containers, because you can define strict ID mappings from one user to the user in the container. So it becomes easier to access those files as well. And I'll talk a bit more later in the following slides. So in general terms, ID mapping is a file system feature that allows a mount namespace to show a different UID and GID than what it's actually stored on the file. This feature was developed by Christian Brauner and is available in Linux in Linux 5.12 plus, so it's been around for a while now. And an important consideration of the ID map mounts is that the feature was not added for entire user namespaces. Instead, it's more granular and flexible in the sense that you can define an ID mapping for each mount in your system, which can be very powerful. Okay, so next I'm going to talk a little bit about the different scenarios and use cases for ID mapping. As I quickly mentioned before, the first one would be containers. So usually containers need to provide a common root image or base image that needs to be accessed within the container. Now, in the host system, user namespaces are used to provide the isolation for the containers. But still, the containers should be able to access this common or base image with root privileges. That's one of the use cases. So mounting the image with the ID mapping would enable these non-privileged UIDs in the containers to have privileged UIDs and be able to access those common root images within the container. In addition, file sharing also becomes a bit easier with ID mapping because you just need to define different mappings for the UIDs within each container, and you don't necessarily need to change, again, the ownership of the user and the group of the files within each container. You just define the mapping that you want for each mount, and it's done. You have access to the files you need, and in containers, usually to these root images. Okay. Another important use case scenario for ID mapping is related to DAC, or discretionary access control permissions, when sharing files. So here's a scenario. You can have a systemd service that defines a storage directory, which could be a state directory, as we saw in the previous slides. And then we combine this with dynamic users. So the service is going to be running with an unprivileged UID. And then assume that root can create a file on the host namespace with 770 permissions, meaning only root can access this file, and any other unprivileged UID won't have access. However, this is a shared file, so within the system unit namespace, say that it's running with UID 60,000, the systemd service won't be able to read or write to the file since the last 3 bits of the access permissions are not set, right? So one way to solve this problem would be to change the permissions in the host file to 777, right, to give access to all kinds of UIDs in the system, and then in this way the systemd unit will also have access to the share file. But this is not desirable because obviously any unprivileged UID would be able to read or write to the file, so it's not the best solution. Another possibility is to change the ownership of the share file in the host namespace so that the systemd unit can access it. So in the example here, we would change the ownership of the host file from root to 60,000, which is the UID of the systemd service. So in this way, we solved the problem. So before ID mapping was available, these cases were handling by doing recursive CH-owns. One example was systemd homed, which basically keeps consistent access of user files in the home directory. And whenever the home directories did not match, the ownership of the files within the home directory wouldn't match the UID of the user logged in, systemd would have to, in some cases, CH-own the entire home directory to match the UID of the user. As you can imagine, this can be a very slow and inefficient operation, especially if the home directory has a lot of files and subdirectories. So ID mapping comes to the aid for this, because you can basically have a fixed UID in the host namespace mapping to whatever the user UID is for the systemd user. The idea here was to extend the same approach of systemd homed to all the other systemd storage directories, because those can also have multiple files and directories. So ch-owning when a systemd service starts or restarts would be very expensive in some scenarios. Okay, and the last use case is related to ephemeral UIDs. This is also related to the concept of dynamic users. When you have a systemd service with dynamic users, systemd can potentially recycle the same UID after another invocation of the service. So in the example here, again, you have a file in the host namespace, this time with a 60,000 ownership, so that the systemd unit can access it. And let's say that this systemd unit gets restarted, and potentially could be assigned a new UID, say 65,000 on the subsequent restart. So by changing the UID of the systemd unit, now it's running with 65,000, then it loses access to the file again, because again, the files have sticky ownership, so it's still gonna be 60,000, and the systemd unit won't have access anymore to the file. As shown before, I mean, this can be solved with by either changing the permissions of the file in the host to make it accessible by everyone, meaning world writable permissions, or directly ch-owning the file in the host namespace. But neither of those options are usually efficient or optimal, so ID mapping is a pretty nice way to resolve that problem as well, and would take care of these scenarios where you need to, when a systemd unit gets restarted with a different UID. Okay, so this brings me to the actual implementation of ID mapping for systemd storage directories. So in general terms, the feature is when you define a systemd service with dynamic users set to yes, and then you combine it with any other storage directory. And if you have ID mapped enabled in the kernel, then systemd is going to create an ID mapping from the nobody user, which is 65534, to the dynamic UID of the service for each mounted directory. This feature was implemented in systemd version 257, so it's available starting with that version. And then there were some security considerations that were important when implementing this feature. The first one was the choice of the fixed UID in the host. So there were some discussion to either use the nobody user or the root user as the fixed UID in the host namespace. We went with the nobody user just to minimize the possibility of any root exploit or any root escalation, privilege escalation. Since using root would mean that the unprivileged users would get access to the root-owned inodes. So that was why we made the decision of using the nobody user as the fixed UID in the host. And then obviously we are turning off the set UID for the ID map mount, and we're also mounting those with the no exec, so there are no binaries that can be executed within the storage directories. The second thing was backward compatibility for systemd services that already created storage directories on a previous systemd version. In those cases, we continue to do the ch-own for those pre-existing directories, since the ID mapping would apply to newly created directories. Okay. So what's the internal mechanism to apply the ID mappings for these directories? Setting up ID map mounts basically involve the creation of, if you will, a dummy user namespace that would contain the ID mapping tables. So for each directory mount, we would spawn a new user namespace, and in the UID map and GID map files of the user namespace, that's where we would define the actual mapping for the mount. So as you can see in the example here, on the UID map table, we define a mapping from the nobody user, which is the first column of the entry, to the UID of the systemd service, which in this case would be 60,000 for ease of understanding. And the third column is just the range of UIDs that you want to map. In this case, would be just one. The same goes for the GID map file. Once we have the ID mapping tables ready within this dummy user namespace, then we need to associate this namespace with the actual mount. And for this, we use the mount set attr syscall, which has different fields, two of them being the attribute set and attribute clear. So to actually enable ID mapping on the mount, we just need to set the mount attr ID map attribute as part of the attribute set field. And then we just need to point the user NSFD entry to the file descriptor of the user namespace that we have created. And in this way, we will have the mapping ready for the mount. Cool. So next, I'm going to show a pre-recorded demo that I have recorded to kind of show how ID mapping can be used with state directories.
Here, I have an Ubuntu machine with a systemd version that does not support ID mapping yet. First, I will create a sample systemd service, which sends a ping every minute with dynamic users enabled, a sample state directory, and I'll start the unit. We can check that the unit got assigned a dynamic user ID. Right now, the UID is 63750. Looking at the state directory on the host, we can see it is owned by the dynamic user ID. If we enter into the view of the service, we can see that the same UID has been assigned there as well. Let's create a file from the services view using ncenter again, and we can confirm that the same dynamic UID shows in the host namespace. Now, let's modify the service to also use dynamic users, but let's specify a different UID, 65,000, which could happen on any unit restart, since dynamic users implies the use of ephemeral UIDs. And again, let's check the new service UID. Right now, it is 65,000, as we defined before. If we list the files under the state directory on the host, all were changed to ownership to the new UID, using recursive chowns. This would be very inefficient if the directory had a lot of files and subdirectories. Now here, I have a Cameo instance running a recent systemd version and a Linux kernel that supports ID map mounts. Let's create the same sample unit, first with any dynamic UID. Let's check the user ID assigned to the unit. It is 63750. But now, if we look at the user ID in the host namespace, it's the nobody user, or 65534, as expected with ID mapping. Now, let's enter to the unit's view to check a few things. We can first see that the bind-mounted path has now ID mapped enabled. Let's check the user ID of the directory to make sure it's the service's UID. Here we can see the nobody user in the host, as seen before, was mapped to the service's dynamic UID, 63750. Let's create a file in the service's data directory. It has the dynamic user ID. Now let's go back to the host namespace and check the UID of the new file. It's the nobody user, as expected. Finally, let's restart the unit using a different UID, 65,000, just as we did before. We can see that the files still have the nobody user in the host, so the recursive chown was not needed anymore. Let's confirm that the files within the services view are owned by the new dynamic UID. And they are. This demo shows how ID map mounts are now used for systemd state directories, but the same applies to other storage directory types. Thank you.
Okay, cool. So yeah, that was a quick demo. Here we could see how ID mapping was enabled for the state directories. And it provides a way to, again, avoid these recursive chowns that systemd was using before this feature was implemented with the storage directories. Okay, so the second part of the presentation would be about these quotas. So to give some background about it, as the name suggests, this quota is just a mechanism for limiting the amount of disk space that a user or group can use on a file system. As you could imagine, without these limits, a user could easily fill up the entire machine's disk, and that would cause problems for any other user in the system. Currently, most modern file systems already support these quotas. This includes, ext3, ext4, XFS, and BTRFS as well. There are different types of these quotas. The most common ones would be user and group quotas to assign limits to individual users or groups within a system. The one that we're mostly interested in for this talk would be the one of project quotas, which is the third one right there. Project quotas are basically directory tree quotas, meaning that the limits are applied to a given directory and all the files and subdirectories below it. These type of quotas are only available or supported right now in the XFS and ext4 file systems. Okay, so these quotas for the systemd storage directories. As I mentioned before, this feature relies on the availability of project quotas, so this would only work with systemd services that run on an ext4 or XFS file system. And the idea here is to be able to have these limits enforced by different systemd services and also on a per directory type basis. So you could potentially define different quotas for different directory types. You can have one limit for storage directories, another one for cache, etc. This feature is available starting in systemd version 258. And the quotas are defined for the number of disk blocks and also optionally the number of inodes. There are two types of limits that can be established for these quotas, either hard or soft limits. With the hard limits, obviously, the limit cannot be exceeded. With soft limits, they can, but then warnings are issued when you're going above the limit. There are two main requirements to be able to start enforcing these quotas for system services. The first one would be to enable the project quota on your file system. This can be accomplished with the Tune2FS utility. And the second one would be to actually turn on the quotas on the system, again, with the quota on utility. Okay, so in systemd, we've made the distinction between enforcement and accounting directives. The first group of directives would actually enforce the limits. So there are three, one for each directory type. We have the state directory quota, cache, and logs. And runtime here, the runtime directories here is not included because TempFS does not currently support project IDs. You can define either an absolute size limit or a percentage value for these directives. If you pass an absolute limit, then only the number of blocks, the limit for the number of blocks is set. If you pass a percentage value, then the same percent quota is applied to both the number of blocks and inodes for the disk. As I mentioned before, only the hard limits are set in this case because we actually want to enforce those limits. The second category of directives is just for the accounting. So if you establish or if you define these directives in your service, then the limits are not actually enforced. Systemd is just going to track the unit's disk usage without actually enforcing those limits. And the usage will be shown as part of the, if you do a systemctl status of the unit, then the usage of the unit will show there for disk. Okay, so the main mechanism to apply quotas for systemd service was, again, using project IDs. These are basically unsigned 32-bit integers, and systemd defines a predefined range for this that has been reserved, like a pool of project IDs that we take from when defining a new storage directory. The project IDs are unique per service and per directory type. So each file and directory that belongs to the same systemd service and the same directory type, either state, cache, or logs, are going to have the same project ID. And this is how we actually aggregate all the usage for the different directory types. and keep track of that and enforce the limits. The project IDs are set recursively using one of the extended attributes on the file systems, ext4 for example, which is the FSX project ID. And then this is set using an IOCOTL. And the project IDs are only released if neither enforcement nor accounting is needed anymore for the service. The second part, or the second mechanism to enforce these quotas, is using the quota CTL-FD SCaLE, which allows to set the actual limits for the associated project ID. So as you can see on the right, the quota CTL SCaLE depends on this struct, which is the DQ-BLK, which makes available different fields. The ones that are more relevant for this is the first one, the DQB hard limit, which allows to set the limit for the number of blocks, and then the DQB-I hard limit to set the limit for the number of inodes. Okay, so this is the second demo, which again I'll be showing how we can define these quotas for a state directory.
Here, I have a QEMU instance with a systemd version that supports these quotas, and a Linux kernel with a quota module installed. I also have a virtual disk partition of about 500 megs with an ext4 file system. I'm going to do some initial setup to enable quotas on the disk. First, I will enable project quotas on the ext4 file system. I'll use the tune2fs utility for this. And we can confirm that project quotas were enabled. Next, I'm going to mount the disk and move /barlib to it, since I'll be demoing using systemd's state directory. The last setup step would be to turn on project quotas for the mount point with the quota-on utility. Now, I'm going to create a sample systemd service with two state directories called sampledir and sampledir2. We're going to enable quota counting for state directories and set an absolute quota limit of 10 megs. Let's check the status of the service. Since we enabled accounting, we will see the current usage and absolute limit in the output. We can see that the current usage is about 8K and the max limit 10 megs. Let's take a look at the extended attributes of the data directories to show the project IDs assigned to them. We can use the rep quota utility to see a more detailed description. Here, we see that for the assigned project ID, we have a hard limit for the number of disk blocks, which after taking the block size into account is equal to our 10 meg limit. Now, let's create files using ncenter and see if the storage limits are enforced. First, we will create a 5 megabyte file in one of the directories using the dd utility. We can see that the file creation went through and that the project IDs were applied recursively. Now, let's create another file of 20 megabytes to go above the 10 meg limit. This time, we get an error message saying that the quota was exceeded, confirming they were being enforced for the sample service. The limit can also be defined in terms of percentages, in which case the quota is applied to both number of blocks and inodes. Let's change the limit to 10% and restart the service. If we check the status, we can see that the limit is now around 47 megs, which is about 10% of the total disk space. Checking rep quota again, we will see that the same project ID was reused after the restart, since the directories already existed. Since we use percentages, now there's also a hard limit for the number of files or inodes. We could also just keep quota counting but not enforce the limits anymore by commenting out the state directory quota directive. Let's restart the service with this change. In this case, we can see that the project ID is still active, but there are no hard limits set. If we do a systemctl status, it will report just the usage, without the limit. Finally, we can also remove the accounting directive to stop tracking disk usage for the unit. In this case, the project ID has been released, since there is neither tracking nor enforcement of these quotas. This demo showed how these quotas can be used for systemd state directories, but the same applies to cache and log directories as well. Thank you.
Okay, cool. So yeah, that was the demo showing how you can use the different directives that were added for systemd storage directories. Okay, so that pretty much finalizes my talk. Some conclusions about this would be that the first one, ID map mounts provide a safe way for systemd storage directories to avoid doing any recursive chown or even changing the ownership or permissions of files on disk when systemd service starts or restarts, which again could be a very slow and inefficient operation, as systemd was doing with homed, for example, in the past, before ID mapping was enabled in the Linux kernel. For systemd service, this would only apply in units that define dynamic user. And then the second part, obviously, is the one of project quotas that are used to enforce and track these limits for different systemd services. The different quotas can be set for different storage directory types, as we saw. So you could have a per service per directory type quota, and this is only available if your system is running on an ext4 or XFS file system, which are the ones that are pretty common today. So you should be able to create your service and establish the limits that you want for your service. Okay, so yeah, that pretty much concludes the talk. These are some references that will be available once the slides are uploaded. So thank you. Yeah, if there are any questions, I'm happy to take any. Thank you.
Hey, is there a security concern if you had a legacy service that is actually running as nobody? It could write the files that are owned by the systemd managed service.
Yeah, so the question is if there were any security concerns when using the nobody user as the fixed UID. So that was one of the design decisions that was discussed with the upstream maintainers. Nobody seems safe enough given the fact that systemd already has those boundary directories for systemd services that run with dynamic users. So in that sense, the service manager doesn't just randomly create files on systemd units, and any other UID wouldn't be able to access those directories under private. So in that sense, the nobody user seemed like the best option for the fixed UID on the host. Now, the other one was obviously root, which is a little bit more, we were more skeptical using root because there could be cases where you could have root privilege escalations and things like that. So yeah, I mean, with the maintainers, basically we decided to go with nobody. It seemed like the safest option for the fixed UID. Yeah, I think given the fact that we're also mounting without set UIDs set for the mount, the no exec and all the other options for the mount, I think it would be pretty safe to just have it that way in the host. Yeah.
Any other questions? Thank you.
Thank you. Thank you for coming.
Hello? 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 Good? Okay. I talk loudly normally, so I feel like I should be okay. Okay. Oh, really? Hopefully that won't be me. Okay. Cool. Thank you. Say it again? Oh, Jordan Rome. See? It's close enough. Oh, really? Do you think Yakov is still watching? It's too late. Oh, yeah, yeah. Sure, but not yet. All right, almost there. We'll give people a minute, then we'll start. All right, I think it's about 6:15. I think we can get started. Thank you guys for sticking it out to the last talk of the day at the kernel low-level systems track. Nothing says Saturday night like a talk on BPF, so I'll try and keep it interesting for you. So yeah, the talk is about bpftrace, learning to be a language. If you don't know about BPF or bpftrace, that's okay. We'll do some primers as we get started. I guess first things first, who am I? I'm a software engineer at Meta. I've been there for about 8 years, but in the kindness of their hearts, they allow me to work on bpftrace as a maintainer, which is an open source project. And usually for icebreakers, they do the 2 truths and a lie. So, at the end of the talk, I'll reveal which one is true. But yeah, read that and try and figure out which one is the lie. So this talk is a journey talk. We're going to talk about the things that we've done this year to sort of get bpftrace to where it is. I'm also going to be advertising some of the new features and cool things that we've been working on. But we're also going to talk about the challenges that bpftrace has had over the years, and what things it was trying to solve and how that's evolved, some of the pitfalls and issues that users have had, and how we're trying to really move it toward being a real domain-specific language. It's not a general-purpose language, but we're trying to make it more expressive and have it act more like a language. So first of all, what is bpftrace? So it is a CLI tool and kind of a language that allows you to run Linux eBPF programs on your Linux systems. It promotes or does live and fast tracing of the Linux and kernel and user space. And it's a language that's primarily inspired by awk, C, and dtrace. And as I mentioned, it's open source. I think a lot of you were here for Quentin's talk about bpfilter, where he talked about what BPF is. So I'm going to sort of graze over this a little bit. But if you haven't heard of BPF, it is a Linux kernel technology. And as Brendan Gregg describes it, it's like putting JavaScript into the Linux kernel. You get to write these little programs, inject them into the Linux kernel at runtime, and then they just do amazing stuff. So where bpfilter was doing networking, bpftrace is more on the third rung down, where it's doing observability. And bpftrace has been around for quite a long time, at least in tech and sort of BPF years, right? It's been around for about 9 years. This was our old bpftrace logo. It was a nice pink pony, but we got rid of it, unfortunately. And it was created way before other BPF or the sort of standardized BPF features were around, BTF, libbpf co-re, and you really don't need to know what those things are, but it's sort of consideration for what it's been developing and how it's been developing over years, and just sort of to advertise it, it's a little bit old. And it's had a lot of different active maintainers. I don't know, I want to say maybe I was the 10th or 12th maintainer through the course of bpftrace's history. Some have come and left and come back. And a lot of different features have been added to bpftrace over the years, some with really narrow scopes for what they were trying to accomplish. And I'll talk a little bit more about that later in the talk. So what problem was bpftrace, when it was created, what was it trying to solve? And it really depends on who you ask. So, Brendan might say that it was the ultimate systems observability tool, or Lexi might say it abstracts the complicated parts of BPF into a simple DSL, or it's, gives kernel engineers superpowers. And just so you know, none of these are real people. They didn't say any of this stuff. But what problems does bpftrace solve? And the list is a bit long. I'm not going to read all of it, but I'll go through some of the high levels. And it really tries to answer tough questions about your system, especially when your system is in peril. It's nice to have a tool that can get you running up and fast so you can do diagnostics and observability on that system really quickly. and have it be flexible. Another problem is that like raw BPF code has a lot of boilerplate. If you've ever written raw libpf before, you know there's like a kernel component, which is the bpf.c file. There's a user space component that can be written in like, C++, Python, I think Rust, now. And on top of that, like BPF verifier errors are also very difficult to understand and debug if you've ever written raw BPF programs before. So that's like a couple of things that bpftrace is like currently solving for users. And just to give a quick video demo of like what it looks like to run bpftrace on your system, let me just play my little video here. You have to invoke it with sudo because you need those privileges to run BPF. And here we are running a bpftrace script. The thing is tracking new PIDs per second on my system. So this is just printing out, all those new PIDs per second in there and killing the script. So that's all. It's very easy to get started and running up, or get up and running really quickly. This is what a lot of bpftrace scripts look like. It is this simple. Like they are known for one-liners. And we'll sort of like go over the anatomy of this script. But what this particular script does is it counts page faults and it groups them by thread name. So again, if I were to run this, bpftrace script on the CLI, like this would be the output I would get. It would say attaching a single probe, and then when you kill the script, you'd see this aggregate sort of map of thread name and the software faults per thread name. So pretty simple, straightforward. The thing on the far left, so if you've ever worked with awk or dtrace before, like this should look familiar, but like the thing on the left is the probe. So this is the thing that bpftrace is attaching to in the kernel. In this case, it is a software probe. So it's attaching to software page faults, and it's doing it at the rate of 1. So for every page fault, it runs this program. If that were to be like software page faults 100, it would be 1 in every 100 page faults where it would trigger this BPF program to run. And the meat of the program is basically just a map. We are defining a map by that @ token there. And then the key for that map is com, which is a built-in in bpftrace that returns the thread name. So we are sort of creating a map with keys of thread names. And then we're using this another bpftrace built-in called count, where basically every time this function is hit, it will like just add 1 to that counter. So like you can go back, and this slide makes a little more sense now that you know like how that works. And by the way, I mean, it's a pretty small group, so if there's like burning questions or stuff that you really don't understand, like, oh yeah, go ahead. So the question is, why isn't there parentheses where? Oh, it's more like syntactic sugar, so com doesn't take any parameters. You actually can call com with parentheses in bpftrace. Yeah, in bpftrace built-ins, like you can do parentheses or not. Like for built-ins that don't have any arguments, like just the raw name works in the same way. Yeah. Strangely enough, though, count you can't leave out. You have to do the parentheses. So I'll get to some of the weirdness of bpftrace later. But yes, that's a good question. So on top of the things that bpftrace can solve, it can also do a lot, right? Like, so it's a general systems observability tool. It can do performance deep dives, system debugging, user space program tracing. You can collect stacks. You can symbolicate those stacks. We have all sorts of neat CLI visualizations for bpftrace, histograms. Someone recently added, even though it's sort of in the unstable feature, it'll be released, no, I think it's out now. There's like this cool time series feature where you can see how like values change over time as the CLI goes and prints. It's really neat, yeah. I should have a demo of that at some point. The funny thing is though, even though bpftrace can do a lot, not a lot is written in bpftrace. So a lot of problems end up growing out of it, and even the experts, like, you know, the scripts that we keep in the bpftrace repo itself don't really exceed 200 lines of code. And the largest script we found on GitHub was somebody implemented Tetris, actually, in bpftrace, which was really cool. And I think there's a version of Snake out there also. And on GitHub, we did a little bit of searching, and there's really only like 10,000 lines of unique scripts, or 10,000 lines of code for unique scripts of bpftrace on GitHub. So, like, what's the problem? Like, why aren't people writing longer bpftrace scripts? Well, if you read Brendan Gregg's book, and I'm not sure if you have, it's something that was published many years ago, like one of the things he sort of advertises bpftrace for is its one-liners, like as I showed you before. We have even like a one-liners tutorial, but like that's one of the things that's known for, like these terse programs that give you system information. And we probably have like 20 of these or something in the repo. So maybe that's one explanation why we don't have like really long bpftrace scripts in GitHub. Another problem is that it's really just easy to hit a wall in bpftrace. So, you know, users may ask, can I factor out common code that's in multiple probes in bpftrace? Well, not really. Can I use a different type of BPF map? No. Can I access different fields here if the architecture is ARM64? No. What about defining my own struct? What about calling this other kfunct? It's exactly what I need. And then they just end up leaving. And that's kind of the story. And truthfully, it's easy to hit a wall if you're a developer or you're a contributor to bpftrace. So let's go through a little story of trying to add a simple feature in bpftrace. So we had this bpftrace script before where it was aggregating on the thread name. Let's instead aggregate on the cgroup ID instead. Okay. So there is a BPF helper that already exists in the kernel called bpf get current cgroup ID. Like, that's all we need. Like, how hard can this really be? Well, here's a light diagram of how bpftrace works. So similar to a compiler, we take a raw string, we lex it, we parse it, we turn it into an AST. There's like a ton of like passes that happen in that little like, you know, arrow there where I said lots of stuff is happening. We turn it into, or there's like an LLVM code gen layer where we take our AST and the types that we've generated from bpftrace and turn it into LLVM IR, which looks like this. And then we have Clang, you know, compile it, we turn it into BPF bytecode, and that's what gets injected into the verifier. So again, somewhat similar to bpfilter. We're not hand-rolling assembly, but if you've worked with LLVM IR before, it's not that much nicer. It's still very complicated. You still have to think about loads and stores. You still have to think about like memory on the stack, like alignment things. Like it's also a pain to work with. So again, our feature, we are trying to add cgroup ID to bpftrace. Okay, so just a few simple steps, right? We need to add the cgroup ID built-in token to the lexer and parser. We need to add unit tests for it. We need to add code for how to resolve the type of this new built-in. We need to add unit tests for it. Oh, we need to make sure the type interacts properly with other types, right? We need to make sure it's handled in this thing called the resource analyzer, which determines like if we need to save some memory in certain parts of bpftrace. We need to add a unit test for that. We need to add possible feature checks. What if the BPF helper doesn't exist in your kernel version? Well, we should tell the user about it before they try and load it and the kernel verifier rejects it. That would be bad. Add unit tests for that. And then we want to make checks to make sure it works for different probe types. Okay, we'll add unit tests for that. Then we had to have the code gen for it, where we actually call the BPF helper, add unit tests for that, add it to the documentation. Then we add an end-to-end test for that. It's painful, right? Like, this is awful. Like, this is just a little snippet of all the different places in bpftrace codebase where you'd have to, like, incorporate this new feature. And that's the problem, right? Every single feature in bpftrace is a language feature. Like, it's scattered all throughout the code base. You have to write so many tests for it. It is it is a nightmare if you're a new contributor. And this is the reason why a lot of developers basically just don't contribute to bpftrace. I mean, LLVM IR being at the end of it is also just a real kicker, and people don't want to deal with that. And truthfully, it's not just a problem with adding new features. Like, the bpftrace language itself doesn't really compose all that well. Type inference is a little bit sketchy. We have these sort of like internal weird types for some things that don't, work with other things as you think they should. There's no way, like I mentioned, to reduce code duplication. There's tons of tech debt all over the code base. There's no extensibility. And one of the really sad parts is that bpftrace is trailing behind upstream BPF features, right? So there's new features that get landed in the kernel all the time for BPF, like arenas, there's new k-funcs. And unless you go through that awful process, which I just, talked about, you can't use it in bpftrace, right? And that's just sad. And I think users want, we're seeing a little bit of trend up here, right, in the graph of this is time and this is lines of code. And I think people want to write more bpftrace, maybe because of, some of those problems I stated. libbpf is hard, or raw bpf is hard. So how does bpftrace go from a language of one-liners to being a more proper language, something that doesn't get in your way, that's somewhat expressive, and allows you to do the things that you want to do when you're writing observability programs? So of course you have to fix everything, right? And that's what we've been doing over the past year. So let's talk about some of those features that we've added to fix all these things. So first and foremost, we wanted to fix the problem of a lacking of the ability to reduce code duplication. So the simplest thing we decided to add was macros. So here is a bpftrace macro, and it's fairly simple, right? So you define a macro above your bpftrace probes, and then you can just call it and pass parameters to it. And this expands before we actually do the code gen into we just modify the AST and inject that macro code into where it's called. Simple, right? Here's an actual bpftrace macro that is actually in the code base right now. So this is just a little bit more complicated example to give you an idea of the things that you can do once you have macros. So we have variables that are checking things, and it's a lot more complicated. But one of the nice things about bpftrace in the addition of these macros is that even if you write complex macros, you can inspect what they look like. So if you type out your bpftrace script, and it may end up something complicated, you're not sure how macros are getting injected, you can add this -d AST command to bpftrace, and it'll spit out the whole nicely formatted, as if you wrote it yourself, bpftrace AST with all the macros expanded.
These are real list macros. It's not like the C macros that just do straight substitution. You're actually manipulating the AST.
Yeah. And they're a little bit...
Sorry, can you just repeat?
Oh, yeah, sorry. So the question was, these are not C macros that just do string substitution. They're more like Lisp macros where we're actually modifying the AST. And the answer is yes. They're also a little bit smarter about that. So we took this idea of hygienic macros from Rust to prevent accidental mutation of variables in maps. So these need to be explicitly passed in to bpftrace macros in order to modify them in the macro body. So that sort of prevents users from shooting themselves in the foot or doing other weird stuff. So the next thing we wanted to fix in bpftrace was code organization. So up until recently, there was no ability to separate your bpftrace code. Let's say you had, and there really wasn't a reason to, right? There wasn't macros before. But now that you have macros, why not the ability to import other bpftrace scripts that have macros that you can call as if it were a library? Simple, right? So it's a little import statement. That's the library file. You're importing the add one macro. Easy. The other thing we wanted to do is fix our sketchy types. And we did this with BTF. So if you're not familiar with BTF, that's sort of the type language that BPF speaks. It literally stands for BPF type format. And I mentioned that bpftrace wasn't around, or bpftrace was around before BTF really became a big thing. But now we are like pretty much just adopting it like wholeheartedly. And we're also using like a constraint-based solving mechanism for bpftrace. I won't get into that too much. I'm not much of a type theory person myself. This is more me learning about it. But bpftrace is statically typed, but it is inferred. So let's look at this bit of bpftrace code. So if you set 1 to the scratch variable a, this is a unsigned integer of 8 bits. And then the same for -1, except that's a signed integer. And then you have 1 minus 1. That's also a uint8. So does anyone have a guess what the type of D is? Anyone? Well, what size? So that's a good guess, and maybe that's what it should be. In bpftrace right now, that D is an unsigned 64-bit integer. And the reason we're doing that is because right now bpftrace is not smart enough to know how often you call a binary operation. Like if this was inside a loop, right? Like it may easily exceed 16 bits, right? Or something like that. So we're basically just upsizing it to the largest possible integer that bpftrace supports. But the point here is it's semi-non-intuitive, and we were trying to make bpftrace usable without having users like type out the types themselves. So we're trying to be a little flexible with how this works. Yeah, so as I mentioned, bpftrace is statically typed but inferred. We have our own like bespoke internal type system called size type, which I won't get into too much, but it's, basically we're just trying to wrap this whole thing around BTF so it's all much more standardized. And yeah, as I mentioned, getting a proper like type solving algorithm so it all works better. The other thing we really wanted to do, and we've spent a lot of time this year, is fixing the lack of extensibility in bpftrace. And we're doing that with what we call C-interop. So as I showed the import statement before where you're importing another bpftrace script, here you are importing a bpf.c file. So this is a raw bpf.c file. It gets imported and you can call it from your bpftrace script. So this one's not too exciting, but here is one that actually lives in the bpftrace code base now that implements a feature in using bpf.c that gets imported. Right, so we have some like extern definitions of the function just in case these aren't defined in your kernel version, you get an error message that's handled. We do things like built-in memcopy and bpf task release. These built-ins don't exist in the bpftrace code base. They are just in this bpf.c file, and it works because bpftrace will compile this and link it in, and as long as the verifier is somewhat happy with this, like it works with bpftrace script. So this fixes extensibility, right? You no longer have to wait on bpftrace to ship a feature to use something in bpf upstream, right? Like there's no more like blockers for like kfuncs that you want to use, right? It's an escape hatch for more complex logic that bpftrace doesn't support. Oh, go ahead.
So when you import a bpf.c file, does it just like insert it, or is it compiling it into bytecode that is then linked with?
The second thing you said. So the question was, do we insert the bpf.c code into like maybe the AST? No, the answer is bpftrace compiles it and just links it in at the end. And again, like as I mentioned, like some of the developer pains, right? Like you don't have to hand roll LLVM IR anymore. You can just write like familiar, semi-familiar bpf.c code. And this isn't really for the common use case of people like wanting a simple like DSL for writing BPF, but it really like just opens this door for allowing bpftrace to keep up with the BPF ecosystem and make developers who may be familiar with writing bpf.c to have, like I said, an escape hatch for continuing to use bpftrace and what it provides, but not like falling behind or not being able to use a feature that they want. And some compiler things that we've sort of started to adopt this year. So we're starting to fix composability with these two new keywords, or well, sorry, just one keyword, comp time, and then we're also using type introspection. And we'll talk a little bit about that. So like I mentioned, we're doing some like not new, but new to bpftrace, old compiler techniques like branch pruning and constant folding. So let me go back to my type example. So the reason C variable is a uint8 is because these are two integer literals that get folded early in the pipeline. So if you look at the AST, like we print out what the AST looks like through each one of our compiler passes, you'll see it eventually ends up like C equals 0 because we're able to determine at compile time that that will always be 0. And that's why it's a uint8 instead of a uint64. But so yeah, that's an example of some compile time folding that bpftrace has started to implement. Let's look at comp time. This is a keyword that we stole from Zig, I believe. But it's very similar to const_expr. But it's basically saying that the expression to the right of comp time has to be resolvable to something at a literal basically at compile time. So in this case, this is a macro called signal. And what this macro does is it sends a signal to a particular process that bpftrace is tracing. And so what we're doing is we're inspecting whether or not the probe type where signal is called is a kprobe. And if it's not, we fail. So fail is a compile time error. So if we basically realize in the AST that we're going to hit this, we don't even compile to LLVMAR or try and load the program. We fail immediately and be like, okay, you can't use signal if your probe is not a kprobe. And just to give, again, really straightforward example of how this works. So here's someone trying to signal within an interval probe. It sort of gets expanded so where interval gets replaced where probe type was. And then, the compile time folding happens. We see that it's true that interval is not a kprobe. And then, we prune down to fail. Yes, exactly. Yeah. So age-old compiler stuff that, bpftrace is starting to implement, hopefully to the benefit of our users. And let's talk about, let me back up. Okay, so I went forward a little bit to illustrate why else comp time is important. So here is a comp time branch, right? And this is basically saying, like, if I'm on PPC64 architecture, like, I want to access the user symbol at this register, right? And if not, I want to take that register. So look, like this bpftrace script now works on x86 and PPC64. You don't need two scripts. You can just do a comp time expression, and then when you run this script on your command line, depending on the architecture, it'll just do the right thing. Let's talk about some of the type introspection functions that we have for bpftrace. So one is called type info, and this is still a little bit experimental, but it allows us to do cool things with comp time, and I'll show that later. So here's some pretty simple examples where we have a macro that wraps type info, and you pass an expression to isString, and it basically just checks whether or not this type info, which returns a tuple, I believe, is a string type. So this allows like all sorts of type introspection in bpftrace. We have another one called isInteger. Here's the signal macro a little bit expanded. So we had the test for the probe type at the top, which we saw. But we want to do different things inside of our signal macro depending on the type of the expression passed in, right? So here is, again, another comp time expression where we check if the expression is a string. And if it is, we call this other function where we take that string and we turn it into an actual number. So we basically just have like a big map of like, signal names to numbers that we do the conversion. And if it's just a raw integer, we'll take that. And then if it's something else, we get the nice like static assert fail that it needs to be one or the other. And yeah, again, here's that architecture example for comp time. So this also really empowers developers to do a lot more with the bpftrace language and a lot less with the bpftrace code base, right? Like as you start to like expose like type introspection functions and things like comp time and the ability to call out to other bpf.c programs, like they don't have to touch as much in the bpftrace code base. Like you are more like starting to write what looks like a standard library. And that's the thing that we're currently developing. And you'll see if you look in like the Git history for bpftrace, there's a lot of things that have been moved out of the bpftrace code base into standard library functions that are written in pure bpftrace. It's really nice to see. And users can create their own libraries and start to import them. And again, it really just unlocks folks that want to use bpftrace and the latest bpf features and don't have to like go through the trouble of developing it or waiting for a bpftrace release, right? So what problem is bpftrace trying to solve now? Well, I think we really want to try and stick to like our core principle of being like easy and flexible, like system observability. But more so, we want to stay out of the developer's way. We want to like promote composability, extensibility. We want them, to not get confused or just abandon it if they see weird behavior in bpftrace. And maybe like bpftrace is starting to become a bit of a tool chain for BPF programs. Because currently I think like, if you write a raw BPF program, you need the bpf.c file, you need a user space component that needs to be compiled, you need to have something to compile your BPF program, right, with BPF tool. Like it's a long process. So, but if you write it in bpftrace, even write your bpf.c code, as long as you're okay with just like printing things to the command line or exporting like data as like JSON or something, like bpftrace can get you there most of the way. And we're actually in talks right now to sort of figure out how we can extend the user space part of bpftrace. So you can write your own like user space functions that can take your data from your BPF program and do different things with it rather than just like printing it to the command line, for example. And truthfully, there are still some like issues with this, with like having users write their own bpf.c programs. Like it sort of exposes verifier errors potentially to the user, which is bpftrace is really trying to, kind of mask that for users. They don't want them to have to deal with it, so that kind of opens them up to that a little bit. But we think it's worth it in the long run, more or less. And yeah, we just want bpftrace to like be, work across different kernel versions and architectures without you having to consider too much about how that all fits together. bpftrace is about to release version 0.25 right now. It's been around for 9 years. We've never had a bpftrace 1.0. And I think by now from the talk, you can sort of see why, right? Like there was a lot of bespoke features that was sort of like tacked on to bpftrace for different use cases. Like it still felt like a toolbox of different things rather than like a more cohesive language and unit for you to like write BPF programs or observability programs with. Well, we're sort of biting the bullet this year, and we're going to try and launch a bpftrace 1.0 by the end of the year with like these basic principles of having a simplified core language in internals. We want to make it robust and predictable. We want to move a lot of functionality to a standard library, and like I said, have it be user extensible. And we want to have a language contract that we can semi-support forever. There's a lot of breaking changes that go into every bpftrace release, whether we like it or not, and that's just because stuff is old and it doesn't work well together, and we're trying to change that. So look out for bpftrace 1.0 this year. We launched a website, maybe, I think it was earlier last year, but we're doing a lot to improve it. I think it's just like bpftrace.org, I want to say. Yeah, I'll find out that. I think it's at the end. But it's got a lot of like documentation, like our standard libraries in there now, the CLI, the language itself. There's lots of like learning tools of like tutorials. And we recently added a bpftrace playground. This is still experimental, but you can now like works kind of like a REPL, right, online. You can like type in little bpftrace programs. It runs in some faraway server on the cloud somewhere and returns you the result. So that's kind of nifty. We're still working on this though. Yeah, here are the resources for bpftrace. So bpftrace.org. The main repo is there. Called out the playground. And we switched from, I think, Matrix and IRC to Discord recently. So most of the conversation is happening there, and that link is available on the main repo website. And that's all I have. Questions?
Hey, great talk.
Thank
you. Oh shit, I forgot what I was going to ask. No. Oh yes, can you talk a little bit about interoperability with other languages? You say like it's on the talks, right? But or like whatever user space you have in your mind, right? But it's great, but reading the print statement out of to do real work, it's a little bit cumbersome. So
yeah,
what do you guys have in mind?
We're not sure yet. I mean, it's going to probably have to be something pretty like simple to start, because we don't want to have to support a lot of different like user space tool chains. So, probably something like akin to C or something, or maybe it'll be like a bpftrace language, like it'll be a function that's like written in actual bpftrace code itself, but it'll be for like user space output. It's very early stages for this. That's why I don't have a ton of like information for you. But yeah, we're working on it.
Thank you very much for the talk and for bpftrace. I use it a lot. It's great.
Great to hear.
Okay, so I have a question actually about bpftrace. Not the new stuff you talked about, but some of the kind of existing things.
Oh, okay.
So mostly I use it with uprobes for user space stuff.
Mm-hmm.
And a lot of times I want to access like structure elements or something that requires dwarf parsing.
Yes.
And it looks like some of that was in progress. I'm not quite sure where it is. So I'd like to know about looking at elements of structures and structures of structures of structures, and also about using dwarf to do stack unwinding. Do any of those work, or is there plans?
Oh yeah. We got a few things in progress there. Okay, so the question was basically like walking user space structures with bpftrace, right? Possibly with dwarf. So this is a very, very challenging problem. We had tried to support basic like container structures for C++ for a little while. I think I can't remember what library we were importing. But now we use like libdw for some of our dwarf stuff. We're hoping that like with the ability to import bpf.c code yourself, that you'd be able to like walk those structures in C rather than in bpftrace. That's not necessarily like a solution, but it might be a little easier to like do like pointer chasing and some weird stuff that you need to do in C that bpftrace maybe doesn't support in the syntax. There is somebody currently working, and for your second question, there's currently somebody working on a dwarf-based stack unwinding in bpftrace. It's in review right now. We're sort of trying to figure out like what to do with it because it's a bit complicated. You have to basically tell bpftrace what program on your system you want to like unwind in real time, and it has to like go walk the dwarf. It takes a bunch of data from that dwarf and it sticks it into like a BPF map, which then bpftrace accesses at runtime to do the stack walking. But I think that we agree that that feature is going to get in soonish, so be on the lookout for that. And is that because that your programs are compiled without frame pointers?
Yeah, I mean, a lot of times you don't have the choice, right? Because your program depends on which libraries and what other libraries.
Yeah, and that library doesn't have frame pointers. Yes. Yeah, I hear you. Yeah. Yeah, yeah. Yeah. So yeah, soonish. Yes.
Anyone else?
So I thought the previous question was going to be the question I was going to be asking, but it's in a similar vein,
okay.
And it's been a little while since I've used bpftrace, so maybe this is actually a really silly question, but I vaguely remember when working through, like when trying to walk through a struct in the kernel, that was especially tricky, and maybe I was just missing something. I was maybe using an older version, or I was just maybe unaware of it. But I vaguely remember having to either like manually include the definition of the structs, or trying to include files, and that was really painful. And it was like, okay, now I need to do a lot of work to really build this kind of small script that's going to be working with these structs in the kernel. And yeah, has that gotten any better, or is there any plans to do that, or was I just doing something really boneheaded?
No, you were right. That was really not great for a long time. So I mentioned we were like leaning into BTF completely. BTF more or less solves that. So as long as like those kernel structures are available in BTF, you no longer need to import those header files or define your own version of the struct in your bpftrace script. You should just be able to like cast like that argument to like a particular type, and we should be able to resolve it in BTF and just know like all the fields, and you'd be able to access and like drill down for that structure. So hopefully that should just work now, and if it doesn't, please file an issue, but like that's sort of how it should be working.
Okay, so just make sure that the version of bpftrace that I'm using has been compiled with BTF support, and then
I think that should be in bpftrace 24, which is our last release, but we're about to do a new release for 25, and that's definitely in there, but it should be in 24 too.
Okay, awesome.
Yeah.
Thank you.
No problem. Oh, just reminded me that you were asking about dwarf support. We're also going to land a feature in bpftrace that allows you to specify the source line and column for a uprobe, and you can attach to that as long as like it's a valid instruction using like libdw for like doing that parsing.
If you do perf-probe-l, it will renumber the line numbers, like starting from the beginning of the function, which is kind of weird.
Wait, what happened? Sorry.
So right now, you can do that sort of thing with perf.
Oh, okay.
Right, but it does this weird thing. So I'm not saying you should do it, but just a comment.
Yeah.
It does this weird thing where it will renumber the line numbers starting from the beginning of the function. So that's how you do that with perf, but I don't know.
Oh yeah, no, I don't think, I mean, we have some like, for the person who's doing the PR, it has some end-to-end tests where like the actual program being traced, like it has the line number and like it seems to be working.
Yeah,
like,
awesome.
Yeah.
Good, thank you.
No worries. All right. Thank you, everyone, for attending and staying late. Appreciate it.